The time it takes for paint to dry and the temperature of the room are two variables. So are customer wait time and customer satisfaction. When you know how two variables in a project, process, or environment are related, you can gauge how one affects the other. There are three main reasons for evaluating the relationship between two variables in Six Sigma. First is to describe the relationship. When you study the relationship between variables, you learn more about the individual variables and the type of relationship between them. Next is to change or control the value of variables. Evaluating variables gives you a better understanding of how to change or control their values. Later, using designed experiments, values of one variable may be adjusted to achieve desired response from the other. The last reason is to make estimates and predictions about a process. When you understand the correlation between two variables, it could help you make estimates and predictions about a process. Then you can more easily predict trends and make changes to improve the process. When you're evaluating variables, the extent of the relationship between them is called correlation. Correlation shows if a linear association between two variables exists and quantifies the strength of that association. The correlation coefficient is a value that measures correlation. It is expressed as a single value, R, and is a measure of nature and the strength of the relationship between variables ranging from -1 to +1. From your background in Greenbelt content, you should know that a scatter diagram is an exploratory tool that highlights a pattern in plotted data. And this information leads to further analysis of correlation and the correlation coefficient. A scatter diagram is the easiest way to illustrate and categorize relationships between continuous variables. Access the content Interpreting Scatter Diagrams after this video if you wish to review this tool. The variables plotted on a scatter diagram are either dependent variables, also called response variables, or independent variables, also known as explanatory variables or predictors. Plotting each variable on the correct axis of the scatter diagram is important. The dependent variable is always plotted on the vertical or y-axis, and the independent variable on the horizontal or x-axis. For example, something like the price of a used car would be the dependent variable, whereas the mileage on the odometer would be independent. The mileage predicts or explains the sales price. Correctly identifying your dependent and independent variables allows you to accurately plot the variables and then analyze the correlation between them in your scatter diagram. When evaluating scatter diagrams, you need to analyze three characteristics: direction, form, and strength. The direction of the plotted points tells you whether there is a positive or negative correlation between the variables. Rising values from left to right indicate a positive relationship. Falling values from left to right indicate a negative relationship. You might also find no pattern or randomly plotted values. Form is the pattern that the data follows when a line is drawn through the plotted points. Points that follow a straight line suggest a linear relationship. You can use correlation and regression to evaluate this type of relationship. If the form is nonlinear, such as a U-shape, you'll need other tools for evaluation. Finally, you evaluate strength by looking at how closely the values are plotted to a straight line and the slope of the line. If data points are not plotted and there's no slope, then the variables aren't related. When the variables are plotted and fall loosely along a line, then the correlation is weak. If they fall close together and tightly along a sloping line, they represent a strong correlation. So when you plot points on a scatter diagram, you look at the direction, form, and strength to tell you more about the relationship between the variables. For instance, in this example, the direction of these plotted points, rising from left to right, indicates a positive relationship. The form the plotted points follow is a straight line. This suggests a linear relationship. And the strength of the relationship of this scatter diagram is weak, as the variables are plotted and fall loosely along a sloping line. Also, consider this example that exhibits a different set of characteristics. The direction that the plotted points of this scatter diagram take is decreasing from left to right, which indicates a negative relationship. The form of these plotted points is a straight line. This suggests a linear relationship. The strength here is indicated by the points falling close together and tightly along the slope. This represents a strong relationship. Other indications in direction, form, and strength can tell you that perhaps variables aren't related or have nonlinear relationships. For example, with the direction, this scatter diagram's points are plotted in no particular pattern. This indicates that there is no correlation between the variables. Then, if the form that the points take on a scatter diagram is not a straight line, like this U-shape for example, it indicates a nonlinear relationship between the variables. Also, in this example, there is no slope when the data points are plotted, so this indicates that the variables aren't related. The linear relationship between two variables can be shown using a scatter diagram. But a scatter diagram can't quantify the strength and direction of this relationship. You must determine this by using the Pearson correlation coefficient, R. Thinking back to your Greenbelt training, you're probably aware that in order to calculate R, you need a couple of key elements. First, you need N, the number of pairs of data in the dataset. The number of X values or the number of Y values is represented by N. Then you need sigma X, which is the sum of all the X values in the table. Similarly, you need sigma Y, which is the sum of all the Y values in the table. You also need sigma XY, which is the sum of the individual values of the X variable multiplied by the individual values of the Y variable in the table. Then sigma X raised to the power of 2 is the sum of the individual values of the X variable squared. And lastly, you need sigma Y raised to the power of 2, which is the sum of the individual values of the Y variable squared. Access the content regarding correlation coefficients after this video if you would like to review this further. Let's examine an example. A regional school board surveyed students prior to an exam to determine how many hours they actually spent preparing. It then calculated R using the Pearson correlation coefficient. The first step is to survey the data and determine that study time is the independent variable, X, and test results are the dependent variable, Y. You can then calculate the sum of both the X and Y variables, 470 and 639 respectively. The next step is to calculate the square of each of the X values in the study time column. Then add them all up to calculate the sum. This gives a figure of 23,200. Then, calculate the square of each of the Y values in the test result column and the total sum of the column, which is 41,529. Finally, multiply each of the X and Y values and find the sum total, 30,805. You can then input all the values in the table into the formula in order to calculate R. This works out to be 0.88. The Pearson correlation coefficient, or R, can range from -1 to +1. Both extremes illustrate a complete correlation. When R is equal to -1, every movement of one variable causes a consistent and predictable movement in the opposite direction by the other variable. When R is equal to +1, every movement of one variable causes a consistent and predictable movement in the same direction by the other variable. And when R is equal to 0, there is no apparent relationship between the two variables. They move independently of each other. It's rare that your calculations would equate to 0, -1, or +1 exactly. Correlation should be interpreted by relating the size of the coefficient relative to these absolutes, so any values above +0.70 or below -0.70 would be considered a strong correlation. You can initially evaluate correlation by looking at how the points are plotted on a scatter diagram. When R equals +1, a perfect positive is illustrated with points being plotted perfectly in a straight line, rising from left to right. When the R value is closer to +1, it shows a strong positive correlation, and points form tightly around a straight line. An R value that is closer to 0 indicates a weak positive correlation, and points lie further away from the line. A perfect negative, like a perfect positive, is depicted by points plotted along a straight line that decreases from left to right, or R equals -1. A strong negative is shown as a value closer to R equals -1, and a weak negative is a value closer to 0. So when you have a study with a table of values, you can evaluate the relationship and analyze the data by plotting the points on a scatter diagram and working out R with the Pearson correlation coefficient formula. Think back to the regional school board example. Students were surveyed on how many hours they spent preparing for a test, and their percentile scores were analyzed. The test results were then plotted as the dependent variable, y, and the study time in hours as the independent variable, x. On the scatter diagram, the values formed a closely plotted, rising line from left to right, or a strong positive correlation. Correlation was then calculated as R equals 0.88, which also indicated a strong positive. For a different example, consider a study that was done on the work experience of the customer service representatives, or CSR, at a call center. The dependent variable plotted on the y-axis is call length, and the independent variable on the x-axis is the amount of calling experience of the CSR. The scatter diagram pattern indicated a strong negative correlation, as the values were plotted fairly close to a straight line, decreasing from left to right. The correlation was calculated as R equals -0.927, which also reflected a strong negative correlation. In the case of an auto sheet manufacturer, it was important to work out the correlation between thickness and pressure in steel sheets. When the data was plotted, the pattern indicated a loosely plotted line rising from left to right, or a weak positive correlation. The correlation was calculated as R equals 0.401, or a weak positive correlation. When you're calculating the correlation coefficient, you're typically dealing with a sample of a population. But when the correlation coefficient for the entire population is called for, you're looking to find the value ρ. Usually, ρ is unknown, so you have to use the sample value, R, as an estimate. Ideally, your R value will be representative of the correlation coefficient for the entire population. But, to be sure, you need to determine how confidently you can treat R as being representative of ρ. If there's a 95% confidence level or greater for your correlation coefficient, you can predict a range in which the value of ρ will fall, or the confidence interval for a specific correlation coefficient. The confidence interval is usually calculated using statistical software or online calculators. As the black belt of a Six Sigma team at a retail bank, you determine that the loan processing time, expressed in number of business days, and customer satisfaction scores at the bank are correlated. A customer survey by your team reveals that longer loan processing time is generally associated with customer dissatisfaction. You want to analyze the relationship between customer satisfaction scores and loan processing time. Your team puts all the values in a table and uses it to calculate the elements needed for the Pearson correlation coefficient formula. You determine that R equals -0.98, which is considered a strong negative correlation. Your team then plots the data points on a scatter diagram. From the diagram, you determine that the relationship is linear and that a strong negative correlation exists between customer satisfaction and loan processing time. Finally, your team calculates the confidence interval for this correlation value using statistical software. At a confidence level of 95%, when R equals -0.98 and the sample size is 30, the confidence interval is between -0.992 and -0.966. Examining the relationship between variables is important in order to find out more about how they interact. Correlation is the measure of how close this relationship is. You use a scatter diagram to highlight patterns in plotted data between two variables. With this diagram, you can analyze the relationship further by determining its direction, form, and strength. To further analyze correlation and quantify the strength and direction of a variable relationship, you must use the Pearson correlation coefficient equation to calculate R. This value can range from -1 to +1. Based on the value of R, you can classify the relationship between the variables as strong or weak, positive or negative. It's one thing to be able to measure the correlation between two variables, but you also need to bear some other points in mind when analyzing their relationship. You should factor 4 key considerations into your correlation analysis to ensure that it is valid. The first consideration is that correlation is not causation. A relationship is one thing, but cause is something more. The second is that context is critical. Focusing on the big picture can sometimes make the difference in how you analyze the data. The third, the Pearson correlation coefficient, only works for linear relationships, will help you understand the difference in analysis of linear and nonlinear relationships. Finally, the fourth consideration is that the correlation coefficient, R, is highly sensitive to outliers. Each of these considerations will be explained more as the topic continues. The first consideration is that correlation is not causation. In other words, just because two variables are correlated doesn't automatically imply that one causes the other. Two variables can be related, but not necessarily one causes change in the other. Sometimes a close relationship is observed due to both variables being caused by a third factor. When dealing with correlation and causation, you should take certain things into consideration. For instance, correlation is symmetrical and does not imply causation. This means that X correlated with Y is the same as Y correlated with X. While correlation is symmetrical, causation is asymmetrical or directional. Also consider that causation is not reversible. X causes Y. It flows in one direction. For example, a hurricane causes the phone lines to go down. You can't reverse it and say Y causes X. The phone lines going down don't cause a hurricane. Another consideration is causation is often difficult to determine. The case of a third unknown variable could be the actual cause. Situations and variable relationships are often complex and require more analysis. Lastly, consider that correlation can help point to causation. In finding strong correlation between variables, you'll also rule out data that's unrelated and help focus on the relationship that may lead to determining causation. Consider this. An HR analyst discovers that as the rate of pay goes up, the number of employees leaving to go to other companies decreases. The team concludes that there's a strong negative correlation between pay scale and employee turnover. This is an example of correlated variables where there is a causation link. In contrast, a company finds a relationship between pay scale and the number of manufacturing errors. As pay increases, the number of defects decreases. The company, however, determines that as the pay scale increases, employee retention increases. Employees tend to be more experienced doing the same job and therefore make fewer errors. This is an example of correlated variables where there is no clear and direct causation link. 3 relationships can be taken or mistaken for causation. First, genuine causation exists when there is clear and uncomplicated data to support the proposal that X causes Y. An example of genuine causation would be the correlation between long holiday weekends in the summer leading to higher grocery store sales. Next, common response to an unknown variable occurs when both X and Y react the same way to an unseen variable. An example of a common response to an unknown variable would be the correlation between swimming pool sales and bug bites. Both increase and decrease symmetrically, but the variable not taken into consideration is the season of the year. Lastly, confounding is when the effect of one variable, X, on another, Y, is mixed up with the effects of other explanatory variables on Y. For example, you're studying the effects of a new diabetes drug on a group of patients. The study gives a mixed result with significantly reduced blood glucose levels for some of the patients, but not the same for others. Further investigations reveal that patients that responded very well to the drug were also involved in physical activity and were on a diabetic meal plan. You note that a greater level of physical activity and meal plan could have confounded with the effect of the new drug for these patients. In order to establish causation clearly, you must run a designed experiment. The second consideration is that context is critical. You must understand that considering the context in a given situation is critical toward the formation of accurate data analysis. You know that when R measures above plus 0.70 or below negative 0.70, it's considered a strong correlation relative to the absolutes of 0, -1, and +1. But you must take the context of the situation into consideration also. If the measurements of correlation are being used in the context of life and death situations, apparently low or high correlation values will be interpreted and treated differently. Whereas for precision in calibration of instruments or measurements of pharmaceuticals, you would be looking for a high correlation value, as close as possible to -1 or +1. For example, even an apparently low correlation value between the amount of rainfall and frictional force on a runway, say 0.1, may cause enough of a concern for air safety officials to warrant a thorough investigation. Likewise, an apparently high value may not be high given the context. A car's speedometer must be calibrated in order to precisely and accurately measure the car's speed. The manufacturing plant demands a correlation of 0.993, which, given the context, is not as high a value as it would initially seem. The third consideration is that the Pearson correlation coefficient only works for linear relationships. This is important to know because, in a nonlinear relationship, a correlation coefficient, R, with a low or zero value, can still indicate a high association. In other words, a relationship between variables can be very strong, but as the curve is nonlinear, the R coefficient that captures the linear relationship fails to measure this and gives a low correlation score. This point is illustrated, for example, when you have 4 different x and y variables with calculations that all come to the same conclusion, R equals 0.816. But when the individual data is then plotted on 4 scatter diagrams, the relationships are very different. This is because R only recognizes linear relationships between variables. For this reason, plotting the values of the variables using a scatter diagram before calculating the correlation coefficient is advisable. This will help to detect any nonlinearity in the data of which R is not a good measure. The final consideration is that the correlation coefficient is highly sensitive to outliers or extreme values in the data. Outliers can be very misleading, as they skew the correlation coefficient value. When an outlier is identified, investigating the cause is important, as doing so can lead to valuable information or an error that must be fixed. You're studying the correlation between box office collections and the critics' rating scores. The Pearson correlation coefficient calculates a low value of R equals 0.188. When your team plots the data on a scatter diagram, though, you discover an outlier due to a data entry error. On realizing there's been an error, you fix it by correcting the decimal place on the first value so that it reads 130.08. Then you redraw the scatter diagram and do the calculation again. This returns a much higher R value of 0.410. So you can appreciate just how sensitive the correlation coefficient is to an undetected outlier. There are 4 key considerations related to correlation analysis. First, correlation is not causation. 2 variables can be related but not cause one another. You have to be careful not to misinterpret correlation as proof that causation exists. The second key consideration is that context is critical. The context of a situation determines if a correlation is in fact high or not. Third, the Pearson correlation coefficient only works for linear relationships. It's important to plot the variables on a scatter diagram first in order to be able to spot a nonlinear relationship. Finally, the correlation coefficient is highly sensitive to outliers. When an outlier is identified, it is important to investigate the cause, as the error. Predicting a week's worth of weather by looking up at the sky would be a definite challenge. With the correct tools and software, though, you could much more easily determine what's coming and make more accurate predictions. Regression analysis can help you model the relationship between the dependent, response, and independent, explanatory variables and make predictions about the dependent based on values of the independent variable. Suppose you're studying the correlation between loan processing time and customer satisfaction at a bank. Your team creates a scatter diagram from the table of values. Did your team correctly plot the independent variable and the dependent variable? Loan processing time is plotted on the x-axis and is measured in the number of business days a bank employee takes to process a loan application. The independent variable is always plotted on the horizontal axis. So in this case, loan processing time is independent. Customer satisfaction is plotted on the y-axis and reflects the score, on a scale of 1 to 8, that customers assign to the loan application process in a survey. The dependent variable is always plotted on the vertical axis, so customer satisfaction is dependent. The loan processing time explains the customer satisfaction score. When you're assessing the relationship between variables, you first need to determine if it's linear. When you plot the data points on a scatter diagram, they may indicate a linear trend. You can then use linear regression to identify the line of best fit and build a mathematical model for it. This will enable you to predict how the dependent variable, y, will respond to a given value for the independent variable, x. Calculating basic linear regression helps you to predict how the dependent variable value will change if the independent variable does. And having this information helps you to change your process for the better. But what if you discover during data collection that you need to examine multiple independent variables in your process? To account for this possibility, there is both simple and multiple linear regression. Simple linear regression deals with one dependent variable, for example, a person's weight, and one independent variable, like their height. Multiple linear regression deals with one dependent variable, for example, a person's weight, and multiple independent variables, like their age, gender, and height. Suppose you're conducting a study on the factors that affect hourly income of Six Sigma green belts. Depending on the data you've collected, you would either use the simple linear regression model or the multiple linear regression model. If you are studying the correlation between years of education and hourly income of Six Sigma green belts, you're dealing with one dependent and one independent variable and determining simple linear regression. In that case, you use the simple linear regression model. But if you carry out a similar study in which years of work experience and the degree of complexity of past projects are also independent variables, then you're dealing with multiple linear regression. You'll need the multiple linear regression model in that case. In most cases, multiple linear regression calculations are complex, so you need to use statistical software to complete the analysis. You should note that the simple and multiple linear regression models are standard population equations. In other words, they're for an entire population of observations, not just a sample of them. But in practice, you use these formulas for samples to make estimates about the larger population. You can access the job aid Linear Regression Models and Formulas after this video to review the formulas. From your Greenbelt training, you know that simple linear regression is a calculation that relates directly to the line of best fit between two variables. The goals of linear regression are to model the relationship between the dependent and independent variables and make predictions about the dependent variable based on values of the independent variable. Access the content Simple Linear Regression and the Regression Equation after this video for further review. When you create a scatter diagram, you could take a ruler and draw a number of lines through the data points. Each distinct line would have its own linear equation. So you could get a different calculation for each set of dependent and independent values for each line. You need to find a best fit line between all the data points that gives you y values for each x that are representative of the values you observed. Finding such an ideal line may be difficult, but you can find a closest regression line. But even for this line, there will be differences between the calculations or predictions you make using this line and the actual values observed from the sample. This difference, expressed as E, or error, in the linear regression model, may be negative or positive. To determine if one regression line in particular is the best fit line, you would have to calculate all the distances between the data points and the line, called residuals. You would square these distances and add them up. This sum would then be compared against calculations for other lines. Of all the lines being considered, the one that has the least squared value would be the simple regression line. This is the longhand approach to determining the best regression line. You obviously cannot draw hundreds of lines and tables to determine the one with the least squared value. So instead, use the equation for the line of least squares to determine the equation of the best line. The equation for the line of least squares is based on sample estimates. You will note that the equation is similar to the simple linear regression equation, but beta 0 hat and beta 1 hat symbols are used instead of beta 0 and beta 1. Hat values represent sample estimate for the population parameters. Also, there is no E value in this formula because the least squares line assumes having an insignificant value for E. The real work in using this equation is in the calculation of beta 0 hat and beta 1 hat. Whereas these are two different equations to represent population and sample estimates, the population equation and its symbols are sometimes used to refer to sample data as well. The value of y-intercept, the value of y when x is 0, is represented by beta 0 hat. The value of slope of the regression line, the amount y changes when x is increased by 1 unit, is represented by beta 1 hat. So, when it comes to actually calculating simple linear regression, you need to be familiar with the further breakdown of the beta 0 hat and beta 1 hat formulas. Suppose you're studying the correlation between years of education and hourly income in Six Sigma green belts. To calculate a simple regression line from the data sample, you use the table of values as your starting point. You calculate the elements of the simple regression formula from the data in your table. Follow along as the calculations are discussed. First, you find all the squared values for the x variables. Next, you calculate the xy value for each variable pairing. Finally, you find the sum of all x values, y values, x squared values, and xy values to complete your table. To estimate the value of beta 1 from sample data, you use the equation and the values provided from your table to find that beta 1 is equal to 6.07. You then use the beta 0 formula and your values to find that beta 0 is equal to negative 46.2. Once you have the values for beta 1 and beta 0 from your sample data, you can plug them into the linear regression equation to find that y, hourly income, is equal to negative 46.2 plus 6.07 multiplied by x, the number of years of education. This information can be interpreted as the slope is 6.07 and the y-intercept is negative 46.2. So for each year of education a Six Sigma green belt has, her hourly income increases by $6.07. For example, when the years of education value is at 16, her hourly income is at $50.92. Assuming the equation is statistically significant, you can then use the equation to predict a green belt's hourly income for a given number of years of education. For instance, when you plug the value of 10 into the equation as x, you find that y equals 14.5. In other words, if a Six Sigma green belt has 10 years of education, his hourly income is predicted to be $14.50 per hour. However, if you use the value of 15 for x, then y equals 44.85. So, if a Six Sigma green belt has 15 years of education, his hourly income is predicted to be $44.85 per hour. Then, if you use x equals 21 years of education, for example, you will find that y equals 81.27. A Six Sigma green belt with 21 years of education would have an hourly income of $81.27 per hour. You can determine the statistical significance of the regression line, whether or not a linear relationship actually exists between the two variables, using a hypothesis test for its slope. If the slope is 0 or the regression line is flat, no relationship exists. However, if the slope is not 0, the regression line is not flat and a relationship does exist between the two variables. You calculate test statistic t for the hypothesis test. you need to calculate elements of this formula separately. For example, you can find the values for SXY and SYY by using the table of x and y values and specific formulas. Within these formulas, x and y are the values listed for the dependent and independent variables, and n is the sample size. You just need a brief overview of that formula at this point. You'll learn more about how to use it later. Regression analysis can help you model the relationship between the dependent and independent variables and make predictions about the dependent based on values of the independent variable. Simple linear regression deals with one dependent and one independent variable. Multiple linear regression deals with one dependent variable and multiple independent variables. The equation for the line of least squares is used to determine the equation for the best fit line. When you calculate simple linear regression, you need to be familiar with the further breakdown of the beta 0 and beta 1 formulas. Once you know those values, you can interpret the slope and the y-intercept of the data and make predictions about the dependent variable based on the independent variable value. In regression analysis, you use the line of least squares equation to model the relationship between the dependent and independent variables and make predictions about the dependent based on values of the independent variable. Once you've reached this point in your analysis, you need to carry out a hypothesis test. A hypothesis test helps validate an assumption about key characteristics of a population based on sample data. In an ideal situation, this validation may require examining the entire population. However, it's often cost-prohibitive or even impossible to examine all data in a population. A more practical approach is to examine a representative sample to draw conclusions about the population. If sample data is not consistent with the hypothesis about the population is rejected. In a regression analysis, the hypothesis tests the slope, beta 1, of the equation. If the line is flat and the slope, beta 1, is equal to 0, then no relationship exists between the variables. But if the line is not flat and the slope, beta 1, is not equal to 0, then a relationship may exist between them. During your Greenbelt training, you learned that in order to provide backup to your statistics, you need to be able to quantify the strength of your findings. Access the content, key concepts, and the process of hypothesis testing after this video for further review. Hypothesis testing helps determine whether chance is a plausible explanation of an experimental finding. Hypothesis testing for regression statistics allows you to determine whether or not the relationship between independent variable x and the dependent variable y is merely a chance event. As you know, all types of hypothesis testing, including testing for regression statistics, involve 5 steps. The first step is to define the business problem, essentially identifying exactly what you want the test to tell you. Next is to establish the hypotheses. Once you have defined the question you need answered, you can establish your 2 hypotheses, the null hypothesis and the alternative hypothesis. The third step is to determine the test parameters. Once you have defined your 2 hypotheses, you can then decide how to conduct your hypothesis test and within what test parameters. And the final step is to interpret the results of your calculations. You must compare your test statistic to the critical value method, or the p-value with alpha, the p-value method, and use this information as the basis for rejecting or failing to reject the null hypothesis. But before you begin carrying out the 5 steps, you must make sure that a number of conditions have been met. One condition is that given a particular value for x, the distribution of the y values is normally distributed. Another condition is that the distribution of y values has constant variance. And lastly, that the y values are random and independent. You can gain a greater understanding of how to perform a hypothesis test for regression statistics when you understand how its steps are applied in a business situation. Follow along with the example as it unfolds and examine how each step is applied along the way. Consider this: you work for a large retail bank and are analyzing the bank's current loan processing time. You feel that the loan processing time and customer satisfaction scores are correlated. Your team conducts a customer survey which reveals that longer loan processing time at the bank is generally associated with increased customer dissatisfaction. You need to conduct a hypothesis test to determine whether or not the independent variable, loan processing time, is a useful predictor of the dependent variable, customer satisfaction scores. You have collected 30 samples of loan processing time and customer satisfaction scores. From this data, you plot the scatter diagram and the best fit line and complete your correlation analysis. Using the least squares method, the regression equation is determined as y equals 9.91 minus 0.516x. In other words, the customer satisfaction score when loan processing time is 0 is equal to 9.91. So for every incremental day of loan processing time, the customer satisfaction score drops by 0.516 points. From this regression equation, you then know that beta 1 equals negative 0.516 and beta 0 equals 9.91. With your definition of the business problem in place, you can move on to the second step. You need to establish the hypotheses that will be used in your regression statistics. The null and alternative hypotheses are mutually exclusive. If one is true, the other has to be false. Your goal is to reject or fail to reject the null hypothesis by proving or failing to prove the alternative hypothesis. The null hypothesis, H0, assumes that any change in your dependent variable following a change in the independent variable happens due to random chance. It states that the slope beta 1 of the regression line is equal to 0. On the other hand, the alternative hypothesis, H subscript A, assumes that any change in the dependent variable following a change in the independent variable is real and statistically significant. It states that the slope beta 1 of the regression line is not equal to 0. So if beta 1 is equal to 0, that means that the slope is 0, which means there is no relationship and the equation is not a useful predictor. From the regression equation in the loan processing example, you know that y equals 9.91 minus 0.516x, and more specifically, that beta 1 equals negative 0.516. In this case, then, beta 1 does not equal 0, so a relationship exists, and the equation is a useful predictor of the customer satisfaction score. Once you have determined your null and alternative hypotheses, you can then determine your test parameters, which is step 3. You have to ask yourself a few key questions when determining your test parameters. Ask, should you use a one-tailed or two-tailed test? What is the degree of freedom? And what significance level, alpha, is needed? You use a one-tailed test when the test hypothesis is only supported by results in one specific direction. For example, you want to test a hypothesis if the average cycle time is actually reduced after a process improvement project, or mean diameter of spring valves has increased over a period of time. You use a two-tailed test when the test hypothesis is supported by results in either direction. For example, you want to test a hypothesis if the cycle time has changed significantly, either more or less, after a process improvement drive. In a two-tailed hypothesis test for regression line, you'll reject your null hypothesis if the test statistic for your slope data is in the critical regions on either side. As in the loan processing example, the alternative hypothesis, H subscript A, states that the slope beta 1 is not equal to 0. So you can follow the general rule that if your alternative hypothesis has a not equal to sign, you can use a two-tailed test. If the alternative hypothesis had a less than sign, you would use a one-tailed test to the left. If the alternative hypothesis had a greater than sign, you would use a one-tailed test to the right. The next parameter to consider is the degree of freedom. Every test has a different way to calculate the degree of freedom statistic. The most common is where the total data points, n minus 2, equals the degree of freedom. For example, in the loan processing example, if the sample size, or n, is 30, then you would calculate the degree of freedom as 30 minus 2, or 28. The final parameter to consider is the significance level, or alpha. Alpha represents the level of statistical significance that is required in order to reject the null hypothesis. Many tests use 0.05 as the alpha, while some intend to detect very small differences, so they may use 0.01 or even 0.001. In the case where your hypothesis test produces a statistically significant result, a cutoff point is established, which is equal to the test critical value for a given alpha and degrees of freedom. So if your test statistic is greater than the critical value, you reject the null hypothesis, and if it is less than the critical value, you fail to reject the null. In another method, p-value is determined using the test data and is compared against the alpha value. If the p-value for a hypothesis test is less than the alpha value, the null hypothesis is rejected. If the p-value for a hypothesis test is more than the alpha value, you fail to reject the null. In a two-tailed test, if your alpha value is 0.05, you divide it by 2 to give you a value of 0.025 in either direction. This means that you're willing to take a 2.5% risk of rejecting a null hypothesis that is actually true. In a two-tailed test, you reject the null hypothesis if the observed test statistic is either higher than the positive critical value or lower than the negative critical value. So, to put it in perspective, you and your Six Sigma team have completed the first 3 steps in your analysis of the bank's current loan processing time. Let's recap each step. For step 1, you define the business problem. Does a statistically significant relationship exist between loan processing time and customer satisfaction, as described by the slope of the regression line? For step 2, you establish the null hypothesis as the slope of the regression line, beta 1, is equal to 0, and the alternative hypothesis as beta 1 is not equal to 0. And for step 3, you determine your test parameters. The degree of freedom was calculated as 30 minus 2, or 28. The alpha for this type of test is 0.05. And you are trying to determine if the observed sample statistic is higher than the positive critical value or lower than the negative critical value. So this means it's a two-tailed test. The fourth step of your hypothesis test is to calculate the test statistic for regression. The test statistic, or t-statistic, indicates whether your sample data is consistent with the population mean or whether it's less than or greater than the mean. The t-statistic especially comes in handy when you have a small sample size and you are trying to make sure it's a reliable representation of the larger population. This information will later be your basis for rejecting or failing to reject the null hypothesis. The formula you use to find the t-statistic is called the regression hypothesis test statistic. It's broken down further into 3 elements, including beta 1, which is the slope of the regression line. Another element of the t-statistic formula is the standard deviation of errors formula, which contains separate calculations for SYY and SXY based on values from your data. The final element is SXX, which is also calculated from the data table. The symbol beta is used to represent key population characteristics, called parameters, intercept and slope in this case, for the population regression line. Because populations are often extremely large or even infinite, it is often impractical to measure every element of the population. For this reason, samples are drawn and their properties are generalized to represent the broader population. A beta with a hat above is used to denote the sample estimate of the population parameters. Recall the study on the correlation between loan processing time and customer service scores at a bank. You have a table of values to work with and the regression hypothesis test statistic formula. Follow the steps for calculating the elements of the formula and working out the t-statistic. Beginning with your data table, you can add 3 columns to the right and start calculating the values for sigma x, sigma y, sigma x raised to the power of 2, sigma y raised to the power of 2, and sigma xy. The value for n is the sample size, which you can also determine from your data table. You can then calculate the value for beta 1 using the equation to find the slope of the regression line. In this case, it works out as negative 0.516. You should also calculate the sum of squares at this point. SXX is an element of the regression hypothesis test statistic formula. This works out to be 109.22. You calculate SXY to be negative 56.38, and SYY works out as 30.06. Once you have all of the elements, you can plug them first into the formula for standard deviation of error. This gives a value of 0.186. Then you can take the value for standard deviation of error, SXX, and beta 1, and work out the t-statistic, negative 28.99. Now that you have the t-statistic, you can turn to the final step of the hypothesis test, interpreting the results. If you are using the critical value method, then besides calculating the test statistic, you also have to find the cutoff points or the critical values for your data. Next, you compare your test statistic against these critical values. If you are using the p-value method, you calculate the p-value from your data and compare this against the alpha value for your test. Then, from these comparisons, you decide whether to reject or fail to reject the null hypothesis. The test critical value is obtained from the t-distribution table by cross-referencing the degree of freedom and alpha to find the assigned test critical value. Often, these calculations are done using software or online calculators. And the p-value is found from the t-distribution table by using the degree of freedom and the test statistic. It's imperative that you use an appropriate t-distribution table for finding the p-values, as many tables give values for one-tailed tests only. In most cases, the p-value is found using software or an online calculator. The p-value method is most commonly used in Six Sigma. You can access the job aid t-distribution table after this video if you want to review the full table and an explanation of how to arrive at a p-value. You compare the p-value that you find from the t-distribution table to alpha. If your p-value is smaller than alpha, the test result is considered significant and the null hypothesis is rejected. You can also gauge the significance of your test result by how much smaller the p-value is than alpha. Your p-value is an indicator of the strength of evidence for rejecting the null hypothesis. Consider again the banking study on loan processing time and customer service scores. During Step 2, you established the null hypothesis and the alternative hypothesis. Then, in Step 3, you determined your test parameters. Next, you determined that the test statistic value is 28.99, ignoring the negative sign, using the regression hypothesis test statistic formula. You must then find the degree of freedom of 28 on the t-distribution table. You follow along the row until you find a value as close as possible to your t-statistic, which in this case is 3.674. At the top of that column, you find that the p-value for 3.674 is 0.0005. So the p-value for your test statistic, 28.99, would actually be much lower than 0.0005. With an alpha value of 0.05 and a p-value of less than 0.0005, you know the p-value is definitely less than the alpha value. You can then conclude that this result is extremely statistically significant, and you can reject the null hypothesis. If you chose to use the t-critical value method, you would locate the degree of freedom of 28 and the alpha value of 0.025. Remember, this is a two-tailed test. That would give you a t-critical value of 2.048. Since a t-statistic of 28.99 is greater than a t-critical value of 2.048, the null hypothesis is rejected. In other words, you can assume that there is enough statistical evidence to show that the relationship is not by chance, and that the independent variable, loan processing time, is a useful predictor of the dependent variable, customer satisfaction scores. A hypothesis test for regression statistics is the best way to test the accuracy of your data. Hypothesis testing allows you to determine if the independent variable is a good and accurate predictor of how the dependent variable will react. Hypothesis testing for regression statistics involves 5 steps. Step 1 is to define the business problem. Step 2 is to establish the null and alternative hypotheses. Then, in Step 3, you determine the test parameters. Step 4 requires the calculation of the test statistic. With this value, you can use the t-distribution table to find the p-value. Once you have your p-value, you can move on to step 5 and interpret your results. If your p-value is less than alpha, you can conclude it is statistically significant and reject the null hypothesis. In regression analysis, to this point, you've carried out a test to quantify the relationship between two variables and to predict the trend the values will take. You have also carried out a test on the accuracy of your data to determine if the independent variable is a good predictor of the dependent variable's response. Once you've come this far in regression analysis, the next step is determining if the simple linear regression model is effective using the coefficient of determination r squared. This is expressed as the square of the Pearson correlation coefficient r. R squared is a value between 1 and 0. It's usually expressed as a percentage. R squared describes the amount of variation in the response or dependent variable that is explained by the predictor or the independent variable. It's an evaluation of the errors in the regression model through an analysis of the residuals in the scatter diagram. Think about this. Residuals are the difference between the observed values and the predicted values. They are measured as the distance between the plotted points in a scatter diagram and the regression line. Small residuals mean less error, meaning the independent variable explains a larger percentage of the dependent variable's response. Long residuals mean more errors and the percentage is less. As the r-squared value increases, the residuals decrease. An r-squared value of 100% would be displayed as points plotted perfectly along the regression line. The closer you move to an r-squared value of 100%, the more effective the regression model is. A high r-squared value indicates that almost the entire variation in the dependent variable is explained by the independent variable. R-squared values can range from high to medium to low, and by analyzing these values, you can gauge how effective the regression model is. Consider some examples of the resulting r-squared value and interpretation for each range. Regarding the high range, in a retail bank study, you calculated that the correlation of customer satisfaction and loan processing time was equal to -0.984. The r-squared value, then, is 96.8%, which is considered high. This means almost the entire variation in the dependent variable is explained by the independent variable. The residuals are short, and this is an effective regression model. With the medium range, in a study on the correlation between box office collections and movie critics' ratings, R is equal to 0.766. The r-squared value is then calculated to be 58.7%, which is in the medium range. This means only some of the variation in the dependent variable is explained by the independent variable. The residuals are medium length, and this is only a moderately effective regression model. Then, with a low range, during an auto sheet manufacturing study, you calculate the correlation of plate thickness and applied pressure as 0.401. The r-squared value, then, is 16.1%, a low value. This means almost none of the variation in the dependent variable is explained by the independent variable. The residuals are long, and this is not an effective regression model. While r-squared is effective, it's also limited. It can only measure some part of the total variability in the dependent or response variable. As a result, a high r-squared value may not always guarantee that the model fits the data best. For that reason, you need something more, and residual analysis is the answer. Residual or graphical residual analysis evaluates the errors in the regression model by plotting the residuals in different ways and then extracting information from these graphical representations. You should note, though, that this analysis is usually carried out using statistical software. Graphical residual analysis has an advantage over r-squared or other numerical methods because it can sometimes illustrate the relationship between the model and the sample data more clearly, indicating various factors. Other methods can be limited to one calculation, measuring one thing, which is expressed by one number. Within regression analysis, there are 3 assumptions made about errors and, in turn, 3 types of residual tests. The test for normality of residuals uses a normal probability plot graph to analyze and interpret the results. It is based on the assumption that errors follow a normal distribution. The test for randomness of order is based on the assumption that errors are random and independent and are not affected by the order in which the data is collected. This test uses a graph that plots residuals versus the order they are observed. And the test of constant variance is based on the assumption that errors have constant variance over all values of x. This test plots the residuals versus the fitted values to identify unusual patterns across the data. These tests are used to assess the validity of a regression model. If the model fails any of these residual tests, the result of your analysis may be misleading you in some way. The first type of test is the test for normality of residuals. The assumption that errors, or residuals, will follow a normal distribution can be examined by plotting the residuals on a normal probability plot graph. This graph plots the residual values as points on the x-axis and the normal values on the y-axis. If residuals follow a normal distribution, they should plot closely along a rising straight line. If this trend is not evident, the model is not valid. A fail of the test for normality would be indicated by a clear curve in the data or by an evident outlier. These types of displays would indicate that the residuals do not follow a normal distribution. Remember the previous examples of high and low range R-squared values? The retail bank study on customer satisfaction scores and loan processing time had a high R-squared value of 96.8%. The plate thickness versus applied pressure example had a low R-squared value of 16.1%. The normal probability plot of customer satisfaction score residuals follows a normal distribution as the points are plotted along a straight line. And the normal probability plot of the plate thickness residuals appears as an S shape, which indicates a non-normal distribution and a fail of the test for normality of residuals. The second test for residuals you'll be using to validate the model is the test for randomness and independence of order and time. This test is based on the assumption that residuals are random and independent. They are not affected by the order in which the data is taken. The test for randomness graph plots the residual values as points on the y-axis and the order the residuals were observed on the x-axis. If the order of your plotted points appears to be totally random with no apparent pattern, the residuals are independent of each other. If a pattern is detected, though, it may mean that the residuals are not independent of each other. Common patterns you may find are residuals decreasing as the order they are observed increases, or a sudden change in the residual values from left to right and low to high. Your overall goal is to ensure you have a random sample of the larger population. If, in fact, your sample was not selected randomly, this test will indicate that. You plot the residuals against the order that the data was collected on a test for randomness graph and try to find a pattern. If you determine that the residuals are not independent of each other, it may be an indication of a problem during data collection or of an error that needs fixing. You need to double-check your data collection methods to ensure this is not the case before deciding that the model is not valid based on this residual test. Recall again the example of the retail bank study on customer satisfaction scores and loan processing time. In contrast, this time compare the results with that of a study on the correlation between call length and the work experience of a customer service representative, CSR. In the test for randomness graph for the loan processing and customer satisfaction study, the order of the plotted points appears to be random. Since there is no apparent pattern, the residuals are independent of each other, which indicates a valid model. In the test for randomness graph for the call length and CSR experience study, the order of the plotted points appears to be random until there is a sudden shift in the residual values from left to right and low to high. Since there is a pattern, the residuals are not independent of each other, which indicates a model that is not valid. The third assumption is that errors have a constant variance across all values of x. For this, you need the test of constant variance. First, you must find the fitted values using the regression equation. Then you plot the residuals versus the fitted values on a graph. The residual values must always be on the vertical axis and the fitted values on the horizontal axis. When the plotted points appear scattered evenly around the zero line for all values of x, having no unusual patterns, it indicates a valid regression model. But if the spread of plotted data points increases or decreases with the fitted values, then there may be non-constant variance. You may also identify outliers during this test. Either of these patterns would indicate a fail of the test for constant variance and a regression model that is not valid. Consider once more the example of the bank study on customer satisfaction and loan processing time. To compare constant variance graphs, you examine the results from a study on Greenbelt hourly income and amount of education. On the hourly income test for constant variance graph, the plotted points increase as fitted values increase, which indicates non-constant variance. This means the regression model is not valid. On the customer satisfaction test for constant variance graph, the residuals versus the fitted values appear more constantly spread around the zero line, having no unusual patterns, which indicates a valid regression model. On the hourly income test for constant variance graph, the plotted points increase as fitted values increase, which indicates non-constant variance. This means the regression model is not valid. Once you have carried out the 3 tests and all the assumptions about the errors have been met, you know that you're working with a valid regression model that will make accurate predictions. If any one of those tests had failed, though, you would then need to re-examine the data you collected and how you collected it. Access the job aid Graphical Residual Analysis after this video to review the 3 residual analysis tests and examples of the graphical trends. The coefficient of determination, R squared, is used to determine if the simple linear regression model is effective. R squared is expressed as a percentage and is calculated as the square of the Pearson correlation coefficient, R. However, R squared is limited, so graphical residual analysis provides a deeper analysis. You can use 3 types of residual tests to assess the validity of a regression model: the test for normality of residuals, the test for randomness and independence of order and time, and the test of constant variance across all values of x. You typically perform these tests using statistical software. In completing these 3 tests, you can validate the regression model and feel confident that your associated results will provide accurate. Consider your daily life and things that happen during the run of a business day. How often do you make an estimate or a decision based purely on a guess? When surmising the outcome of a situation, anyone can make a guess. But if you've got a bit of information to back you up, then you can make an educated guess and get closer to estimating the true outcome. Hypothesis testing is a way to statistically test your educated guess or your hypothesis based on the sample data you collected from a larger population. The test for statistical significance is hypothesis testing, all leading to a conclusion of either rejecting or failing to reject the null hypothesis. During the analyze stage, theories and premises about key elements in a process, its performance and variables, and their interrelationships are closely examined using hypothesis tests. Once you reach this step, you can use the results to pinpoint the root cause of your process failure and find ways to implement a solution. Hypothesis testing is necessary in Six Sigma. You use a random sample from a data population to estimate characteristics of the entire population and make process changes. Hypothesis testing allows you to make sound decisions based on solid results. You can carry out 2 types of hypothesis tests on the population mean, comparing a population mean to a specified value and comparing 2 or more population means. A hypothesis test that compares a population's mean to a specified value, such as a specification limit or performance goal, helps you decide whether the mean is different from that set value. A hypothesis test that compares 2 or more population means is used in order to decide whether they are statistically different. Hypothesis tests can be carried out on other aspects of the population besides mean, such as proportion or variance. Likewise, there are different types of hypothesis tests. Proportions can be similarly compared with a specified value or with each other, and the same is true for variances. As well, the formulas used in tests for means, proportions, and variances are different, so you must be prepared to recognize the type of hypothesis test required and be able to apply the right one. From your Greenbelt training, you're familiar with the concept of hypothesis testing. The null hypothesis and alternative hypothesis are the centerpiece of any hypothesis test. The hypothesis acts as the statement that your test and results aim to either prove or disprove, or reject or fail to reject. Access the content hypothesis tests after the video to review the elements of a hypothesis test. The null hypothesis uses the equal to statement because it hypothesizes the comparison of a population parameter with a standard or between two or more populations. It can also sometimes be expressed with less than or equal to, or greater than or equal to. It assumes that any observations are the result of chance or random variation. The alternative hypothesis assumes a corresponding comparison of not equal to, or greater than or less than between two or more populations. It assumes that any observations are real and not the result of chance or random variation. You're also familiar with the concept of one- and two-tailed tests. A one-tailed test is used to determine whether your values are greater than a set value, one-tailed to the right, or less than a set value, one-tailed to the left. You use a two-tailed test to determine whether your results come within set boundaries or critical values, or fall below or above your possible results. Consider this situation. The director of the Consumer Loans Department at a retail bank claims that the average auto loan processing time is 8.9 business days. Your process improvement team thinks that the processing time has decreased since application processing was automated. To test the hypothesis with 95% confidence that the current processing time is less than the claim, you record 20 samples of processing time. So, what type of test is required here? You'd use a two-tailed test if you wanted to find out whether the loan processing time is significantly more or less than 8.9 days, and you'd use a one-tailed test to the right if you were trying to determine whether you'd increased loan processing time. However, because you're trying to find out if you have reduced the loan processing time, that is, that the processing time is less than the standard, you should use a one-tailed test to the left. Once you've reached this part of hypothesis testing, you've determined your alpha level. So you need to conclude your hypothesis by using either the critical value method or the p-value method. You find the test statistic using your collected data and a formula depending on which type of test you are conducting, z-test, t-test, f-test, or chi-square. You then find the critical value by using the degree of freedom and significance level, alpha, with the correct associated table. If you locate the test statistic on the x-axis, it will either fall within the critical range, in which case you'd conclude that your result was statistically significant, or it would fall outside the critical range, in which case you'd conclude that your results could be due to chance, so you wouldn't reject the null hypothesis. Within Six Sigma, each test statistic has an associated p-value. The p-value is the risk of finding a test statistic that is at least as extreme as the value found from the sample data when the null hypothesis is true. You compare the p-value to alpha. If your p-value is less than or equal to alpha, you can conclude that your results are statistically significant and reject the null hypothesis. A p-value is typically the output when hypothesis tests are done using statistical software, but you can also find it manually. Establishing statistical significance is vitally important for your conclusions. It adds strength to your findings by guaranteeing that the results are real and not by chance. To fully grasp the importance of alpha risk and beta risk, you need to understand the role each plays in hypothesis testing. The most risk you're willing to take in rejecting the null hypothesis when it's actually true is known as alpha risk. It occurs when the alternative hypothesis is accepted due to an overreaction or when there's not enough statistical evidence to support the alternative hypothesis, but it's accepted anyway. This situation is usually related to a type 1 error. The most common alpha value is 0.05, or a 5% possibility that the results are due to chance and that rejecting the null hypothesis would be an incorrect decision. The beta risk is the risk of failing to reject the null hypothesis when it's actually false and should be rejected. This situation is related to a type 2 error and can be thought of as underreacting, or when there is statistical evidence to support the alternative hypothesis, but instead it's ignored. The most common beta risk is 0.10. In other words, there is a 10% possibility that the results are due to chance, the alternative hypothesis is true, and that failing to reject the null hypothesis would be incorrect. You can also use alpha and beta to find other elements of your test, such as the confidence level using 1 minus alpha and the power using 1 minus beta. When you use an alpha value of 0.05 or 5%, you can determine with 95% confidence that the population mean will fall within the confidence interval. In most cases, the analyst determines alpha based on the degree of risk that can be tolerated. If the value falls outside the interval, there is an alpha % chance of it doing so. In the case of 0.05 alpha, it's a 5% chance that the population mean is not within the confidence interval. There is also an alpha % chance that the results are due to chance and your conclusion to reject the null hypothesis is wrong. Recall the consumer loans example. The average processing time is 8.9 business days. You use the data to test the hypothesis that processing time is less, so you use a one-tailed test to the left. In this case, alpha is 0.05. So the confidence level is equal to 1 minus alpha, which is 0.95, or a 95% confidence level that the population mean will fall within the confidence interval. There is also a 5% chance that your conclusion to reject the null hypothesis is wrong. As you know, statistical results are based on a sample of the larger population, so there's always a chance that the results are incorrect. When this occurs, they're called sampling errors, but unlike other types of errors, these can't be corrected. There are two types of errors, type 1 and type 2. Type 1 errors are most often associated with alpha risk and occur when you reject a null hypothesis that is actually correct. The consequence of this error may be making changes to your process unnecessarily. In contrast, type 2 errors occur when you fail to reject a null hypothesis that is actually incorrect and are most often associated with beta risk. The consequence of this error is failing to detect defects to make necessary changes to your process. You are examining a bolt manufacturing line to ensure all bolts are meeting ISO specifications of threading that is twice the diameter of the bolt plus 1/2 inch. You measure a sample of completed bolts for thread length. The probability that you reject sample bolts even though they meet specification limits is your alpha risk. A type 1 error could occur if you reject the null hypothesis when it's actually true. The consequence of making this error could be concluding that your manufacturing line is flawed and proceeding to make changes to the process unnecessarily. Conversely, the probability of your sample passing all quality checks when in fact bolts are being produced outside the specification limits is your beta risk. A type 2 error could occur if you fail to reject the null hypothesis when it is false and should have been rejected. The consequence of making this error would be concluding that your manufacturing line is working well and neglecting to make changes to the process. The power of a hypothesis test is also something to consider when planning your study. Power is the probability that you'll make the correct conclusion and reject the null hypothesis when it's false. It's desirable to have a high-powered test as you want to find statistical significance when it exists. The factors that affect the power of a test include sample size, effect size, population variability, and alpha. Power and alpha are related as increasing alpha decreases beta. Since power is calculated by 1 minus beta, if you increase alpha, you also increase the power of a test. The maximum power a test can have is 1, whereas the minimum value is 0. From your prior Six Sigma knowledge, you already know that sample size affects the power of a test very strongly. In other words, increasing sample size increases the power of a test and vice versa. In addition to sample size, there are other determinants of the power of a test as well. When you estimate population characteristics from samples, you are bound to make errors. This is called sampling error. A hypothesis test is exposed to the same risk when it attempts to test a theory about the entire population based on a sample. The significance level quantifies the risk associated with type 1 error. That is, you reject a null hypothesis when it's actually correct. Access the content Risk and Significance in Hypothesis Testing after the video for a review of this content. The probability of the beta error is not a value set by the experimenter, but found through a series of complicated calculations. So a power analysis should be carried out while planning a study, not after that fact. This will help strike a balance among all the factors that affect power and ensure the most sensitive test feasible. Apart from the sample size, 3 other factors affect the power of a hypothesis test: effect size, population variation, and alpha. You need to consider the effect size or the minimal detectable difference between the groups being compared in a hypothesis test. A distribution shows how an increase in effect size brings an increase in power, with all other factors remaining constant. Increasing the difference between the population means increases the power of the test and the probability of detection. Population variation, or the spread of data from the mean, also affects power. The higher the variation in the population data, the harder it is to detect the difference, and so the power decreases. Also, the effect of variability is related to the effect of sample size, since the more variable the data, the larger the sample size that will be needed to detect a given effect. Finally, alpha also affects power. Type 1 and 2 errors are interdependent, so it's important to select an alpha that is appropriate for your study goals. You also need to keep in mind that alpha accommodates an appropriate power. As alpha increases, so does power. It's important to familiarize yourself with the terminology, but also to understand the 5 integral elements of the process of hypothesis testing: null and alternative hypotheses, one-tailed or two-tailed tests, alpha and beta, type 1 and type 2 errors, and finally, confidence and power. The key hypothesis testing concepts are all used to interpret your results in a hypothesis test. The null hypothesis and alternative hypothesis act as a basis for you to define your business problem. Then you can determine the test parameters of a one-tailed or two-tailed test and the appropriate values for alpha and beta. Then, in finding your results, you must take into account the confidence level and power of your test and the probability of type 1 and type 2 errors occurring. In carrying out the process of hypothesis testing correctly, you can better guarantee the strength of your results. In the age of the GPS, have you ever chosen the shortest route option only to find that during rush hour traffic it takes the longest? While the route with the least amount of miles has statistical significance, it doesn't have practical significance. There's a chance that your hypothesis test results won't be representative of the population. It's important to know whether your results are real or simply by chance. So, choosing the level of acceptable risk you're willing to take before you begin the test is key. In testing, you must have statistical significance. It's the only way to guarantee the strength of your results and support your decisions. In business, though, you also need to have practical significance to back up the decisions you make. Statistical significance ensures that your results are not by chance. The purpose of your data is to support this theory. Determining statistical significance adds strength to the decisions you make based on those results. Practical significance is necessary when the real-world elements, such as cost or time, come into play. Decisions can't be made solely on statistical significance. For practical purposes, you should choose values for significance level, alpha, and power, 1 minus beta, by carefully considering the consequences of making a type 1 and type 2 error. Just as changing the sample size changes the power and significance level of a test, choosing different alpha levels also affects the result of your test. The traditional value for critical significance, or alpha, is 0.05, but you can also choose a lower or higher level, such as 0.01 or 0.1, depending on what the business situation is. You set the risk level to make the statistical significance more or less sensitive to change. By setting a more stringent alpha level, which decreases the probability of making a type 1 error, you increase the likelihood of making a type 2 error. When setting the alpha level, You need to make a good compromise between the likelihood of making type 1 and type 2 errors. When you calculate the test statistic and find the associated p-value, you compare this to alpha. If the p-value is less than alpha, your results are statistically significant. You have to determine the appropriate level of alpha, high alpha or low alpha, based on the degree of risk that can be tolerated for your test of committing type 1 error. You could choose a high value, for example 0.1, in a situation where there are no catastrophic risks and the financial consequences of a type 1 error are low. Your test will be less sensitive, but it'll be easier to determine whether your results are statistically significant. You could choose a low value, for example 0.001, in a situation where the consequences of type 1 error may adversely affect human health and safety, or a catastrophic loss is involved. A low alpha level means less risk and that your test is more sensitive. Consider a study on the effect of a new insulin on glucose level in high-risk diabetes patients. You want to test the hypothesis that the average glucose level in the control group patients went down after taking the recommended dosage of the insulin. You choose a traditional alpha of 0.05. Using a table with the degree of freedom and test statistic, you find that the p-value is less than 0.05, and you reject the null hypothesis to conclude that the effect is significant in favor of the manufacturer. However, considering the huge consequence of the drug on human life, you want to minimize the risk of accepting a significant effect when there's actually none, so you decide to use a lower alpha value, say 0.001, for your test. Now, when you compare the same p-value against a smaller alpha, you determine that the effect is not statistically significant. You reduced the chances of incorrectly assuming the effect as significant in favor of the patient's health and well-being. Now, consider another study on an improved frozen yogurt flavor. You choose an alpha of 0.1. The results, while important, do not bear catastrophic consequences. Using statistical software, you find the p-value easily falls below 0.1. The results are statistically significant, and you reject the null hypothesis. You're willing to take more risk with a less sensitive test, so it's easier to prove statistical significance. Practical significance should be considered when setting an alpha level for statistical significance. You want to find a balance so you don't find that your results are practically but not statistically significant. And just because results are statistically significant doesn't mean they're practically significant. Finally, an important test where the results turn out not to have statistical significance isn't necessarily evidence that there's no relationship between the variables. Now, when you're considering a statistically significant process change, it's important to think about the situation and ask yourself some questions. First, is the statistically significant process change also practically significant? Also, does the new process cost more? Is the new process more dangerous? And is the new process worth the risk? Finally, will this change make a real difference to the process? Besides setting the correct level of alpha, the sample size you choose can also affect statistical significance. A small sample size means there's the possibility that a large difference won't be deemed statistically significant. Or if you choose a large sample size, you could find that a very small difference is interpreted as statistically significant even if it's not practical. Think of it this way. If you have only a small sample size, then the possibility of finding a combination of the values that would indicate a strong relationship between the variables is high. On the other hand, if a relationship between the variables exists, although small, the only real way to observe it would be in a large sample of the population. If statistical significance is borderline for your results, such as a p-value of 0.052 when alpha is 0.05, you'll need to carefully consider the sample size that was tested. Before conducting a hypothesis test, you must decide on the level of acceptable risk you are willing to take. Statistical significance ensures that your results are not by chance and that your data is solid. Practical significance is also necessary when elements such as cost or time come into play. Decisions can't be made just based on statistical significance. It's important to note that you set the risk level to make the statistical significance more or less sensitive to changes. Traditional alpha is 0.05, but you can also set alpha as 0.01 or even 0.001. Concepts are often taught using a given sample size, and then the learner is asked to determine the critical values for that sample size. But in practice, ideally, you would do the reverse. Start with the desired alpha and beta risk and calculate the sample size needed to reach this level of confidence and power. Determining sample size is critical, as too large samples may waste time, resources, or money, while too small samples may lead to inaccurate results. Although this task is typically done by statistical software, there are formulas that enable you to calculate the appropriate sample size for a given power level. You need to consider three things when determining your sample size: the variation in the sample or population, the minimum value that is to be detected between the population means, and the desired alpha and beta risk. Let's consider an example. The variation in the sample or population that you're trying to determine is an increase in your production output if you increase the speed of your manufacturing line. The minimum value to be detected between the population means is a mean shift of 20 units per day. You also choose the desired alpha risk of 0.05 and beta risk of 0.1. Don't forget, you set the level of alpha that's most appropriate for the test you are conducting. So it's important to consider the power of your test as well, as the two factors are interrelated. A number of factors affect the power of a test, including alpha. Power and alpha are related, as increasing alpha decreases beta. Since power is calculated by 1 minus beta, if you increase alpha, you also increase the power of a test. The power of a hypothesis test is the probability that you will make the correct conclusion and reject the null hypothesis when it's false. It's desirable to have a high-powered test, as you want to find statistical significance when it exists. So, when you're estimating a population parameter from a sample statistic, the margin of error value represents how closely your sample actually estimates the population. When you calculate margin of error, you discover that increasing the sample size improves the precision of your estimate and decreases the margin of error. When you know margin of error, confidence level, and standard deviation of the population, you can rearrange the formula to find your sample size, n. This will give you the number of items that should be in the sample. This is based on the z-value associated with the desired confidence level, the standard deviation, and the margin of error, and assuming your variables are normally distributed. Access the job aid distribution tables after the video to access the z-distribution table. The sample size, n, is always rounded up to the next whole number, as rounding down would not calculate within the right margin of error. The critical value, z alpha divided by 2, is the positive z-value at the boundary of alpha in the right tail of a two-tailed test. The population standard deviation is represented by sigma, and uppercase E is the margin of error. Sample size is critical when using the margin of error formula. If your sample size is less than 30, you must know the population standard deviation, sigma, or a fair estimate of it to use this formula. When your sample size, n, is greater than or equal to 30, you can use S in place of sigma, as the sample standard deviation can safely estimate the population standard deviation for a large sample, where S is the sample standard deviation. Think about this scenario. You're conducting a study for the local cable TV provider on how much time a family spends watching TV per week. You need to find out how many families you need to survey by calculating the appropriate sample size. You want a 95% confidence level within 2 hours per week margin of error. The last survey the company conducted had a population standard deviation, or sigma value, of 22 hours per week. A confidence level of 95% means alpha is 0.05. You work out the critical value to the right of 0 and the left of the boundary of alpha in the right tail to 0.475. You then access the z-distribution table to find that 0.475 is a z-value of 1.96. The margin of error is 2, and sigma is 22. This calculates to a sample size of 464.8336 families. You round that number up to 465 families, as rounding down to 464 wouldn't allow you to reach the margin of error value of 2. With this sample, you'll be 95% confident that the sample mean will fall within 2 hours of the true population of TV viewing. Where the standard deviation is unknown and the sample size is less than 30, you can use the confidence intervals for means formula to calculate the margin of error as a range instead of a single value. In the formula, the value of x bar is the sample mean, and you use the sample standard deviation, S, as an estimate for the population standard deviation, sigma. Instead of a z-value, you use the t-value from the t-distribution table. A t-value is larger than a z-value, which compensates for not knowing the population standard deviation and the small sample size. The value of n is the sample size, which for this formula is always less than or equal to 30. Access the job aid distribution tables after the video to access the t-distribution table. To find the t-value, you calculate the degrees of freedom with n-1, where n is your sample size. You then cross-reference the associated degrees of freedom and alpha to find the t-value. If you have binomially distributed data, you rearrange the confidence interval for proportions formula to find the appropriate sample size. It's calculated using the appropriate z-value, proportion rate, and desired proportion interval. To calculate proportion, you also need to know the number of defects in the sample. So, depending on your data and the information you have at your disposal, you can choose the correct formula to calculate the sample size within the appropriate margin of error. Access the job aid calculating sample size formulas after the video to access the 3 formulas. The ideal way to calculate the sample size is to start with the desired alpha and beta risk. Alpha is related to margin of error, since a smaller alpha risk means a smaller margin of error, and margin of error is, in turn, related to sample size. When you know your margin of error, confidence level, and standard deviation of the population, you can rearrange the margin of error formula to find your sample size. When you're trying to pinpoint the root cause of your process failure and find ways to implement a solution, you collect data and carry out hypothesis tests. But it's impossible to collect data on an entire population, so you use sample statistics and make predictions based on your estimations of the population parameters. The process of statistical inference is accomplished through hypothesis testing and estimating. In hypothesis testing, you analyze a sample to test a theory about a population. Hypothesis testing is the more comprehensive approach, but increasingly, estimation is being used in support of and in conjunction with hypothesis testing. There are 2 types of estimates, point estimates and interval estimates. Point estimates are used to find a single value to estimate a population parameter, for example, the mean. Consider this. You conduct a survey of 2,000 people from across the country on whether they are for or against universal health care. Your results show that 1,100 out of 2,000 are for it. The population parameter in this case refers to all the people in the country. The sample is the 2,000 people you surveyed. The point estimate, then, is the proportion of people who are for universal health care. So, the statistic you reach from the sample of the population is 55% of all the people in the country are for universal health care. Point estimates can be classified as unbiased or efficient. When the mean of all possible sample statistic values is equal to the corresponding population parameter, you have an unbiased estimator. When you can make an estimation of a population parameter using more than one possible sample statistic, the statistic with the smaller variance is considered the efficient estimator. So, to clarify the meaning of unbiased with an example, the average of a sample's distribution of means is equal to the population mean. The sample mean is considered an unbiased estimator for the population mean as a result of the central limit theorem. You should note that the mean of sampling distribution of standard deviation is not equal to the population standard deviation. So, the sample standard deviation, S, is considered to be a biased estimator of population standard deviation, sigma. Also, a sample's distribution of mean and median both have the same mean, the population mean. but the variance of the sampling distribution of means is smaller than that of the sampling distribution of medians. So the sample mean is an efficient estimator of the population mean. You should note that efficiency and bias aren't necessarily connected. An unbiased estimator can be very efficient. However, you'll rarely find a biased estimator that is also the most efficient. For example, the sample mean is both an unbiased and efficient estimator of the population mean. The sample mean is more efficient than another statistic, such as median, as the variance of the sampling distribution of mean is much less than that of the median. The sample median is an inefficient estimator of population mean. Similarly, the average of the sampling distribution of sample means equals the population means, so this is also an unbiased estimator of the population mean. On the other hand, the sampling distribution of variances is a biased estimator of population variance. So while point estimates offer the best results in certain testing situations, there's also a downside. When calculating point estimates, sampling error can have an impact on the calculated values. In many cases, point estimates don't exactly equal the population parameter in a sample. So you need another technique to determine how good the estimate is. In that case, you calculate a range or interval estimates so that the chances of error are minimized. So, to clarify, when calculating point estimates, you assume that the value equals the actual population parameter. Or you can collect a number of samples and find the mean of each sample, knowing that eventually the average of the averages will equal the population parameter. Simplest of all, you could calculate a confidence interval, since its construction is a less cumbersome way to estimate a population value without taking many repeated samples. A confidence interval allows you to calculate a range within which the population parameter is likely to fall a certain percentage of the time. The range usually spans from a lower confidence limit to an upper confidence limit, and the percentage is stated as a level of confidence, which is calculated as 1 minus alpha. You can use confidence intervals to check a number of things: the variability of sample statistics, whether a target value falls within the natural variation of a process, or whether two samples originate from the same population. The concept of confidence is always interchangeable with the concept of risk. As you know, the most common confidence level is 95%. In other words, an alpha value of 0.05 calculated by 1 minus alpha to equal 0.95 and expressed as a percentage. Depending on the situation, you could also use a confidence level of 99% or 90%. As the confidence level increases, so does the range of the confidence interval. The level of alpha that you choose is the level of risk you are willing to take that your true population parameter will fail to fall within the interval. So, when you have a test with a 95% confidence level, you also are willing to take a 5% chance that your value will fall outside the calculated range. You should note that the correct way to express confidence intervals in words is by stating the confidence level percentage and the interval in which the value is expected to fall with that confidence. For example, you could state, at the 95% confidence level, we estimate that the population mean is between 1,050 and 1,185. You should not state, 95% of the values will fall within the range, as this is a common misinterpretation of confidence intervals. Another use of confidence intervals is to examine differences between a population mean and a target value. For example, a pharmaceutical company has a new drug to treat high cholesterol. You want to determine whether the drug improves cholesterol levels to the healthy target level of 200 milligrams per deciliter. Sample data is collected, the confidence level is set at 95%, and the confidence interval is calculated as between 195 and 210 milligrams per deciliter. You then check whether the target value falls within your confidence interval. If it doesn't, the sample is from a population with a mean that's different from the target value. If the target value does fall within your confidence interval, you know that the sample is from a population with a mean that's the same as the target value. In this case, the target value of 200 milligrams per deciliter is within the confidence interval. You conclude that, at the 95% confidence level, the drug is decreasing cholesterol levels to between 195 and 210 milligrams per deciliter. To this point, in statistical circles, theorists have viewed hypothesis testing and confidence intervals as two distinct approaches. But the two are increasingly being considered complementary in inferential statistics and being used in support of and in conjunction with each other. So you can use a confidence interval when you want to estimate a range within which a population parameter will fall. But, depending on the situation, you may also need to make use of tolerance intervals or prediction intervals. When you have a situation where you need to estimate a range within which a certain percentage of population measurements should fall, you'll need to use a tolerance interval. As well, in a situation where you need to estimate future measurements instead of present population parameters, you'll need to use a prediction interval. Tolerance intervals estimate a range, an upper and lower limit of tolerance, within which a certain percentage of each individual measurement in the population should fall. Since the result is based on a sample of the population, for a percentage of the population, it can never reach 100% confidence. So there are two different proportions to refer to, the degree of confidence and the percent coverage. Prediction intervals estimate the future values based on samples that have already been taken. A prediction interval calculates whether the next sample will fall within a set range with a reference to a degree of confidence. You must know the sample mean and standard deviation based on the background data of your sample size, n. In order to use each estimation type to the best of its potential, you need to understand the conceptual differences between confidence, prediction, and tolerance intervals. Confidence intervals only apply to population parameters, not individual values. Confidence intervals can be used to find out what range the mean of a population will fall within, or how this interval compares to a target value. The correct way to express confidence intervals in words is by stating the confidence level percentage and the interval in which the population parameter value is expected to fall with that confidence. Tolerance intervals estimate the tolerance range to a degree of confidence for a certain percentage of the population, called a percent coverage. It tells you what individual values should be versus what they could be or might be in the future. Tolerance intervals are calculated differently than confidence intervals, as alpha represents the percent coverage rather than the level of confidence. It is most useful in compliance monitoring when you are trying to stay within specification limits. The correct way to express tolerance intervals in words is by stating the degree of confidence and the percent coverage. For example, I am 95% confident that 90% of the population will fall within the range specified by the tolerance interval. For example, you're working for a bolt manufacturer ensuring ISO compliance on bolt threading. Your main concern is that bolts are over the maximum threading length. The tolerance interval accounts for some high values, as the calculated tolerance interval may still be lower than the maximum standard limit. But if you find the upper limit of your tolerance interval to be higher than your standard for conformance, there is a high probability that the process or product is in violation. Finally, prediction intervals estimate future values based on present or past values with reference being made to a degree of confidence. Prediction intervals can predict conformity or nonconformity ahead of time and require as few as one sample, so it's useful for detection monitoring. It can predict the interval within which a single future observation will fall. More specifically, it can predict, for a given x, the y value of the next experiment. The correct way to express prediction intervals in words is by stating, I have 95% confidence that the single future observation will fall within the range specified by the prediction interval. Consider this scenario. You're conducting a study on air quality. You want to be able to compare compliance air quality levels, pollution-free air, with air quality samples. You also want to be able to monitor air quality in specific areas over time. So, to compare compliance values to a sample, you have to determine whether the air sample has come from the same pollution-free air quality area. If so, the upper prediction limit should be greater than or equal to the data collected from the pollution-free area. But in a situation when the data falls above the upper prediction limits, it's indicative of polluted air quality. If you're instead comparing current air quality samples to future samples from the same area, Then the prediction interval gives a range of values within which future samples collected from that same area should fall. Any data collected in the future, which does not fall within that specified range, indicates that a once pollution-free area is now polluted. The process of statistical inference is accomplished through hypothesis testing and estimating. The two types of estimates are point estimates and interval estimates. Point estimates are used to find a single value to estimate a population and can be classified as unbiased or efficient. The three types of interval estimates are confidence, tolerance, and prediction intervals. Confidence intervals allow you to calculate a range within which a population parameter is likely to fall a certain percentage of the time. Tolerance intervals estimate a range within which a certain percentage of each individual measurement in the population should fall. Prediction intervals estimate the future values based on samples that have already been taken. Each type of interval has a specific use and application depending on the type of range. In many cases, you're better off calculating an interval estimate instead of a point estimate purely to minimize error. Point estimates usually don't exactly equal the population parameter in a sample, so an interval estimate, like a confidence interval, allows you to calculate a range within which a population parameter is likely to fall a certain percentage of the time. Typically, you would calculate a confidence interval to check whether a target value falls within the natural variation of a process, or to find out whether two samples originate from the same population. You can also use confidence intervals to examine the differences between a population mean and a target value. You can use 4 formulas to calculate a confidence interval depending on your situation. To use these formulas, you'll need 3 pieces of information: alpha, the standard error of the mean, and the sample mean. To calculate a confidence interval, you need to know the set level of alpha. From this, you can find the associated z-value or t-value depending on the sample size you're working with. Remember, the z-value you are finding for a large sample is based on alpha divided by 2 because you're interested in a range for a two-tailed test, one on each side of the range. For a small sample, you're interested in the t-value or chi-square value associated with alpha. You also need to know the standard error of the mean to calculate a confidence interval. This value is estimated as standard deviation divided by the square root of the sample size. And finally, to work with the formulas to calculate a confidence interval, you need to know the value of the sample mean. Confidence intervals estimate population parameters based on the mean and standard deviation of the sample data. The first confidence intervals for means formula is for small sample sizes, less than 30. Using the confidence level and degrees of freedom, n-1, you find the associated t-value. Then, you calculate the sample mean and sample standard deviation. You calculate the margin of error using half of the formula, and then simply add and subtract the sample mean to find the confidence interval for that mean. When the sample size is large, greater than or equal to 30, you use the formula for large sample sizes to determine the confidence intervals for means. For a large sample, the sample standard deviation may be estimated for the population standard deviation. Using the confidence level and z-table, you find the associated z-value. Then, you calculate the sample mean and standard deviation, as well as the margin of error in the same way as the small sample size formula. You then find the confidence interval for means by adding and subtracting the sample mean. As you know, you can also calculate confidence intervals for other population parameters, like proportions and variances, and these formulas differ from that for means. The confidence intervals for proportion formula is calculated using proportion values. You determine the z-value and population proportion estimate, p, by dividing the number of subjects in the sample that have a certain characteristic by the sample size. This will give you a range into which the proportion of conforming units will fall with the set degree of confidence. Confidence intervals for variation are calculated using values from the chi-square table. So while confidence intervals for means are symmetrical around the sample average, variance calculations are not necessarily so. You find the critical chi-square value from the distribution table and n-1 degrees of freedom. Then, using the formula, you can calculate the confidence interval for variation. You don't have to be concerned with this calculation right now, as chi-square tests will be covered in more detail in a later course. So you choose the appropriate formula depending on sample size and which population parameter is being estimated. Access the job aid intervals formulas after the video to review the confidence intervals for means, confidence intervals for proportion, and confidence intervals for variation formulas. Now that you've learned about the formulas, consider this situation. You're conducting a study for the local cable TV provider on the average amount of time a family spends watching TV per week. The sample size is 465 families, and the sample mean is calculated as 22 hours per week. You set a 95% confidence level with a standard deviation of 2 hours per week. Since the sample size, n, is 465 families, you use the confidence intervals for means formula for large sample sizes. With a confidence level of 95%, the z-value is 1.96. You enter the values into the formula. The sample mean is 22 hours per week and sigma is 2, and calculate the interval. You find the 95% confidence interval for a sample mean of 22 is between 21.818 and 22.182 hours per week of TV watching. You are 95% sure that the true population mean of TV watching is between 21.818 and 22.182 hours per week. Now, if your sample size was small, less than or equal to 30, you'd instead use the confidence intervals for means formula for small samples. As you know from your Greenbelt training, in order to cover the uncertainty associated with the small sample size, you determine and use the t-value with this calculation instead of the z-value. Access the content t-value after the video to review information on the t-value. Now, in a situation where you need to determine a required or set range of values, for example, in compliance monitoring when you're trying to stay within specification limits, you need to calculate a tolerance interval. Tolerance intervals estimate a range within which a certain percentage of all measurements in the population should fall, an upper and lower limit of tolerance. Since a tolerance interval is based on a proportion of the population, it can never reach 100% confidence, so there are two different proportions to make references to: the degree of confidence and the percent coverage, certain proportion of the population. As you're aware, tolerance intervals are calculated differently than confidence intervals. The formula for tolerance intervals is calculated with the sample mean plus or minus the factor to adjust the width of the interval, k, multiplied by the sample standard deviation, s. You can determine the k value in a couple of ways. You can reference a k table, or you can calculate the value using one of two formulas. The table you reference is specific to the desired confidence and coverage percentages. Likewise, the formula you use depends on whether you have a one-tailed or two-tailed test. But these methods are rarely used because k values are usually found using software packages and online calculators. It's important to note that if you're dealing with a one-tailed test, you use the alpha divided by 2 value in determining the k value. Another vital point is that in this formula, alpha represents the percent coverage rather than the level of confidence. You're conducting a study on carbon dioxide levels at the site where a manufacturing plant is expected to be built in the next year. You randomly select 20 samples, and the sample mean amount of carbon dioxide is 357.7 parts per million. The sample standard deviation, S, is 15 parts per million. You want to be 95% confident that 95% of the population will fall within the range specified by the tolerance interval. The test is a two-tailed test, so using software, the k-value calculates to 2.396. The tolerance interval, then, is 321.76 to 393.64 parts per million. You are 95% confident that 95% of all the carbon dioxide levels tested at the site will fall within the range of 321.76 to 393.64 parts per million. These air samples come from pollution-free air, so the levels represent the lower and upper specification limits within which your carbon dioxide levels should always fall. If data collected in the future were to fall above the upper prediction limit, it would indicate high levels of carbon dioxide and polluted air. A confidence interval allows you to calculate a range within which a population parameter is likely to fall a certain percentage of the time. And in comparison to the accuracy of a point estimate, interval estimates also minimize error. Confidence intervals are used to examine the differences between a population mean and a target value. You can use 4 formulas to calculate confidence intervals. Intervals for means formula for small samples, intervals for means formula for large samples, intervals for proportion, and intervals for variation. Tolerance intervals estimate a range within which a certain percentage of all measurements in the population should fall, an upper and lower limit of tolerance. The formula for tolerance intervals is calculated with the sample mean plus or minus the factor to adjust the width of the interval, k, multiplied by the standard deviation, s. The bottom line of most Six Sigma projects during the analyze stage is to gain a thorough understanding of the processes to be examined in order to identify potential points of failure that can then be turned into opportunities for improvement. Hypothesis testing is a process whereby suspected points of failure can be statistically validated using a sample from the overall population of interest. By using sound statistical data analysis tools, hypothesis testing significantly reduces the risk of drawing incorrect conclusions from sample data. So when considering which hypothesis test to use, you must first consider the purpose of your study and then the population parameter to be tested, be it means, proportions, or variances. The hypothesis test for means helps determine if the differences between either a sample mean and a hypothesized value, or between 2 or more sample means, are due to natural variability or real differences. Hypothesis tests for means allow you to accomplish 2 things. First, evaluate claims about the performance or characteristics of a process, product, or service. And second, compare performance before and after an improvement effort. The 3 types of hypothesis tests for means are 1 sample, 2 samples, and more than 2 samples. A 1-sample test for means, also known as a 1-population test for means, compares the mean of a sample from a population against a hypothesized or specified value. This specified value can be an expected or desired value, a historical value, an industry benchmark, or a customer specification. For example, a video game manufacturer finds that the average number of defects per unit produced is equal to its historical average of 3. A 2-sample test for means, also known as a 2-population test for means, compares the means of 2 samples. The 2 samples may or may not be from the same population. For example, supplier A and supplier B provide a large aircraft engine manufacturer with industrial bearings. The supplier wants to compare the average life of each supplier's bearings in terms of hours. You can compare the means of 2 or more samples by using analysis of variance, ANOVA, which is beyond the scope of this course. From your prior Six Sigma experience, you know that 1-sample and 2-sample tests for means can be of 2 types, a t-test or a z-test. When the variance of the larger population is unknown and the sample size is less than 30, a t-test is used to calculate a test statistic. You will then use a t-distribution table and the degrees of freedom to interpret your results. When the variance of the larger population is known, a z-test is used. Even if population variance is not known, you'll recall that the central limit theorem allows you to estimate population parameters using sample statistics when sample size is sufficiently large. Therefore, z-tests are typically used when n is greater than or equal to 30. With this test, you calculate a z-statistic and use a z-table to make your conclusions. Access the content Types of Tests for Means and the job aid Test Statistic Formulas after the video to review t-tests and z-tests and their formulas. Consider this example of a 1-sample hypothesis test for means. The director of the Consumer Loans Department at a bank claims that the average auto loan processing time is 8.9 business days, but the variance is unknown. You think that the processing time has changed since the automation of application processing. To test the hypothesis that the current processing time is different from the claim, 20 samples were recorded. Assuming that the sample data is normally distributed, this is an example of comparing one sample mean with a specified value. Since the sample size is less than 30 and the standard deviation of the population is unknown, you would calculate the test statistic using the one-sample t-test for mean formula. If the standard deviation of the population was known, or the sample size was greater than or equal to 30, you would have used the one-sample z-statistic formula. Now consider this example of a two-sample hypothesis test for means. An auto manufacturer is analyzing the root cause of the variation in the quality of seat belts and their braking strength. Two vendors supply seat belts to the auto manufacturer. You want to determine if there is any difference in the strength of the seat belts and if the first vendor's seat belts are stronger than the second vendor's. You take 15 samples from both vendors and measure the mean amount of force needed to brake them. The population variances are unknown, but it is believed that they are equal for both of the suppliers. In this example, you're comparing two samples and the sample size is 15, so you know you'll use a t-test. But you have to ask yourself an additional question. Are the population variances considered to be equal? In this scenario, they are equal, so you'd use the two-sample t-test for means pooled formula. However, if the population variances were unequal, you'd choose the two-sample t-test for means non-pooled formula. An important point to reiterate before moving forward is that one-sample and two-sample tests for means are parametric tests. Therefore, it's a requirement that the data being tested is normally distributed. For the purposes of this course, you can assume that all given data is normally distributed. Non-parametric tests are available for use when the population doesn't conform to a normal distribution, but they are beyond the scope of this course. To begin the process of hypothesis testing, you need a null hypothesis to be tested. Then you can formulate an analysis plan, analyze sample data according to the plan, reject or fail to reject the null hypothesis, and make a decision based on the test. Usually, a 5-step procedure is adopted for testing a hypothesis to determine if it is to be rejected or not beyond a reasonable doubt. The first step in the hypothesis testing process is to define the business problem, specifically what the test will compare or validate. Then, the second step is to establish the hypotheses. Once you know the problem, you can define the two possible answers by the null and alternative hypotheses. The null hypothesis, H subscript 0, is traditionally the hypothesis of no change. It assumes that any difference between samples results from random variation or noise. The alternative hypothesis, H subscript A, is the hypothesis of change. It assumes that observed difference is real. The third step is to determine test parameters. After establishing your hypotheses, you decide how to conduct your hypothesis test. There are a number of considerations, including selecting the appropriate statistical test, identifying key test considerations such as degrees of freedom and alpha value, conducting sampling, and doing normality checks. After determining the test parameters, the fourth step is to calculate the test statistic, which indicates whether your sample data is consistent with, less than, or greater than the population mean. You'll use the appropriate test for means formula and your sample data to calculate the test statistic. And the last step is to interpret the results. Once you find the critical value or the p-value to which you compare your test statistic or your alpha value, you can determine whether to reject or fail to reject the null hypothesis. If the test statistic is higher than the critical value, you reject the null hypothesis. If the test statistic is lower than the critical value, it means that your finding is not significant and you fail to reject the null hypothesis. As you are aware from your previous Six Sigma experience, steps 3, 4, and 5 of the hypothesis testing procedure may change slightly depending on whether you are using the critical value method or the p-value method. You can use either of the methods to reject or fail to reject a hypothesis for means, but the p-value method is more popular within Six Sigma circles and especially among users of statistical software. Access the content, The Process of Hypothesis Testing, after the video, to review more details on the 5 steps of hypothesis testing. Recall the earlier example about the consumer loans department at a retail bank. The claim is that the average auto loan processing time is 8.9 business days. You begin testing this hypothesis by first defining the business problem in the form of a question that you want the test to answer. In this case, has the auto loan processing time changed since application processing has been automated? Is it now greater than or less than 8.9 business days? The second step is to establish the null and alternative hypotheses. The null hypothesis and alternative hypothesis act as 2 possible answers to the question you wanted answered in step 1. So, in relation to the loan processing example, the null hypothesis states that loan processing time is equal to 8.9 business days, or that nothing has changed. The alternative hypothesis states that loan processing time is not equal to 8.9 business days, or that a change has taken place due to automating the process. Step 3 is to determine your test parameters. Because you aren't specifying the direction of the change in processing time, the alternative hypothesis uses a not equal to sign, requiring a 2-tailed test. You create a plan to collect 20 samples and then calculate the degrees of freedom as 19 times n-1. The population standard deviation is unknown, and you assume the data is normally distributed. You want to test the hypothesis, with 95% confidence, that the current processing time is different from the claim, so alpha is 0.05 and alpha divided by 2 is 0.025. Notice that the alpha value of 0.05 is divided in half between the 2 tails. If the business problem had specified a direction for the change in processing time, the alternative hypothesis would have claimed that the mean was greater than 8.9 if hypothesizing an increase, or less than 8.9 if hypothesizing a decrease. Either one of these alternative hypotheses would call for a 1-tailed test. Moving on to the 4th step, you then calculate the test statistic. After you have determined your test parameters, you must choose the appropriate formula. The correct formula for the loan processing example is the 1-sample t-test for mean. The mean from 20 samples is calculated from the data table to be 8.54 business days. The sample standard deviation is found to be 2.96. You also know that the specified value you are comparing the sample mean to is 8.9 business days. When you input the values, you get a t-statistic of 0.54. The absolute value of the test statistic is used in this and other examples in this course. The 5th and final step is to interpret the results. To apply the critical method when interpreting this example, you use a t-distribution table and cross-reference the degrees of freedom and the 2-tailed test alpha divided by 2 value. If the critical value is less than the test statistic, your findings are significant and you reject the null hypothesis. Because the test statistic value of 0.54 was less than the critical value of 2.093, you failed to reject the null hypothesis. There isn't sufficient evidence to say that the loan processing time has changed due to automation, and the claim that the current processing time is 8.9 days holds true with a 95% level of confidence. If you choose to interpret your results using the p-value method, then you would typically do so using statistical software. Essentially, the software calculates the alpha value that would be associated with the test statistic you found. If it is greater than the alpha you set for the test, you would fail to reject the null hypothesis. If you had used a table to manually find the p-value, you would find that your test statistic value of 0.54 corresponds with a p-value close to 0.30, much higher than the acceptable alpha risk level. Hence, you fail to reject the null hypothesis. Evaluating the results in practical terms is also important during the interpretation step. You need to ensure that your results have practical significance as well as statistical significance before implementing any process changes. You may encounter situations when you need an alternative to the 1-sample t-test, namely when you know the variance of the larger population or have a sample that is equal to or greater than 30. In such cases, you'd use a 1-sample z-test for means. With a z-test, you calculate a z-statistic and use a z-table to interpret the results and make your conclusion. A working example provides an easier illustration of a z-test for means. Consider this. An exotic seed producer has recently changed from hand packaging to an automated system. The company claims that the average weight of a packet of seeds is 1.5 grams. You think the new machine may not be calibrated correctly, and the average weight of a packet of seeds has changed. In Step 1, you define the business problem, and in Step 2, you establish the hypotheses. So, during Step 1, you state the business problem in the form of a question. Has the average weight of a packet of seeds changed? During Step 2, you establish the hypotheses. The null hypothesis states that seed packet weight is equal to 1.50 grams. The alternative hypothesis states that seed packet weight is not equal to 1.50 grams. In Step 3, determine the parameters. You compare the sample mean to the claim that the mean weight of a seed packet is 1.50 grams to determine if the machine has been calibrated correctly. The alternative hypothesis states that the packet weight is not equal to 1.50 grams, implying a two-tailed test. You choose a random sample of 75 and assume the data is normally distributed. Alpha is set at 0.10 to be 90% confident that the producer's claim is incorrect before rejecting the null hypothesis. Step 4 involves calculating the test statistic. Since you have one sample group and a large sample size, the correct formula is the one-sample z-test for means. The mean from 75 samples is 1.48 grams. The population's standard deviation is 0.20. The claimed mean is 1.50 grams. When you input the values, you find that the test statistic, z, equals 0.869. With the test statistic of 0.869, alpha of 0.10, and alpha divided by 2 of 0.05 for a two-tailed test, you use an online p-value calculator to calculate a p-value of 0.3848. If the p-value had been less than alpha, the findings would have been significant and you'd have rejected the null hypothesis. However, since this p-value is greater than the alpha divided by 2 value of 0.05, you fail to reject the null hypothesis and conclude that the current seed packet weight does not differ significantly from 1.50 with 90% confidence. You could also have used the critical value method in the 5th step to interpret the results. The value for alpha was previously set at 0.10 for a 90% confidence level. The corresponding critical value, then, is 1.645. Since the test statistic of 0.869 is less than the critical value, your findings are not significant and you fail to reject the null hypothesis. In other words, the claim that the average weight of a packet of seeds is 1.5 grams is held valid with 90% confidence. It's important to note that in real-life Six Sigma situations, statistical modeling and calculations are much more complex and are done using software. But since various Six Sigma certifications require you to perform calculations using a simple, non-programmable calculator, straightforward scenarios are given here as examples to help you understand the concepts and do the calculations manually. So you may find a slight numerical difference between the test statistics, p-values, or critical values calculated using software versus those calculated manually. This difference is usually caused by rounding and is not usually significant enough to change the final result. Hypothesis testing statistically validates your claim about a population using sample data. The 3 types of hypothesis tests are a one-sample test for means, a two-sample test for means, and a multiple-sample test for means. One-sample and two-sample tests for means can be one of 2 types, a t-test or a z-test. You choose the appropriate formula based on the size of the sample or whether the population variance is known. A known variance, or a large sample size, calls for a z-test, while an unknown variance and a small sample size calls for a t-test. One-sample tests compare the mean of one population to a specified value, such as an industry benchmark, historical value, or customer specification. A 5-step process is adopted for testing a hypothesis. Define the business problem, establish the null and alternative hypotheses, determine test parameters, calculate the test statistic, and interpret the results. Access the job aid, The Process of Hypothesis Testing, after the video to refer to the 5 steps and the key considerations of hypothesis. Many business problems require you to examine 2 products or processes in order to determine which one is performing better, gives you more value for your dollar, or decreases defects in your process. The best way to make this determination is using a 2-sample test for means. To review, a 1-sample test for means compares the mean of a sample from a population against a hypothesized or specified value. This specified value can be an expected or desired value, a historical value, an industry benchmark, or a customer specification. But a 2-sample test for means compares 2 means, not necessarily from the same population, to determine whether or not there are significant differences between them. The main difference between 1-sample and 2-sample tests for means is the factors that are being compared. For example, a bank has an average loan processing time of 8.9 business days. You believe that the length of time has changed since the process has been automated, so you want to compare a sample mean to the specified value of 8.9 days. To do this, you employ a 1-sample test for means. To illustrate a 2-sample test for means, consider this example. You want to compare the average strength of 2 bolt manufacturers in order to get the best value and choose your primary bolt supplier. Like 1-sample hypothesis tests for means, 2-sample tests can make use of z-tests or t-tests, depending on the available data about population variance and sample size. Likewise, depending on the method most preferred by you or your organization, the tests may employ either the critical value or p-value method. As with the 1-sample test for means, you can follow the same 5 steps of hypothesis testing to complete a 2-sample test. Start with defining the business problem, and then establish the hypotheses. Next, determine the test parameters and calculate the test statistic. And finally, interpret the results. The basic steps of hypothesis testing should be familiar from your background in Greenbelt concepts. This video will focus primarily on issues and calculations specific to a 2-sample test for means. Access the content, The Hypothesis Test for Means process, after the video to review the steps and details of tests for means. When working with a 2-sample test for means, you will need to consider the hypotheses, the test statistic formula, and the distribution of the data. The hypotheses in a 2-sample test for means typically use the equal to symbol for the null hypothesis and can use the not equal to, less than, or greater than symbols for the alternative hypothesis. With a 2-sample test for means, there are 2 conditions to examine and 2 possible formulas to choose from. So it's important to ensure you're applying the right formula, pooled or non-pooled. When performing a 2-sample test for means, you generally assume that the 2 samples are independent, random, and from normally distributed populations. Also, in most cases, you'll assume the 2 samples have unequal variances. As with a 1-sample test for means, you can use a flowchart to help select the correct formula. And like the 1-sample test, when the population variance is known, or n is greater than or equal to 30, the z-test is used. However, when n is less than 30 and you don't know the variance of the population, the t-test is further broken down into 2 formulas, pooled and non-pooled. You can use the 2-sample test for means pooled formula when population variances are unknown but considered to be equal. You use the non-pooled formula when population variances are unknown and considered to be unequal. Consider this example. You're analyzing the root causes of the excessive variation in the quality of an auto manufacturer's seatbelts. Based on the initial analysis, you determine that the problem lies with the seatbelt's braking strength. 2 different suppliers supply the seatbelts. You want to determine if there is any difference in the strength of the seatbelts and if the first supplier's seatbelts are stronger than the second's. You begin by completing Step 1, Step 2, and Step 3 of the 5 hypothesis testing steps. In Step 1, you define the business problem as, is the strength of the seatbelts of supplier A greater than that of supplier B? During Step 2, you determine your null hypothesis to be that supplier A's seatbelt strength is equal to supplier B's seatbelt strength. And so your alternative hypothesis states that supplier A's seatbelt strength is greater than supplier B's seatbelt strength. In step 3, you determine the test parameters by setting alpha at 0.10 and deciding on the critical value method for interpretation. You assume that the populations are normally distributed and the samples are independent. The population variances are unknown, but it's believed that they're equal. You should also calculate the degrees of freedom, df, here, with the simple formula for a two-sample t-test pooled. Since you have two samples, you have to take those into account when finding your df of 28. You add the size of the two samples together and subtract by 2. Since the alternative hypothesis uses the greater than sign, this indicates a one-tailed test to the right. You can then randomly select 15 samples from both suppliers, measure the amount of force needed to break them, and calculate the mean for each sample. The fourth step is to calculate the test statistic. The population variances are unknown but considered to be equal. When you examine the flowchart, you find that with a small sample size and equal variances, you should choose the pooled formula. The pooled formula is broken into two parts: the formula for pooled standard deviation and the main formula for t. The best way to approach this is by calculating the formula for SP first, since SP is an element of the main formula. From the data table, you can calculate the value for n, the mean, and the standard deviation for each sample. First, the formula for pooled standard deviation, SP, is calculated by inputting the values for n and standard deviation for each sample. This results in a value of 2.399. Then you can input the values for SP, the mean for each sample, and the sample sizes into the pooled formula to calculate the test statistic of 5.47. You decide to apply the critical value method, so you use the df of 28 and alpha of 0.10 to find a critical value of 1.313 on the t-distribution table. So, as the test statistic value of 5.47 is more than the critical value of 1.313, you reject the null hypothesis. In other words, at a 0.10 significance level, the data indicates that seatbelts supplied by supplier A can sustain a higher braking force than the seatbelt supplied by supplier B. In a situation where variances are unequal, you would use the two-sample test for means non-pooled formula. There is also a special formula for determining the degrees of freedom for a non-pooled two-sample t-test. Consider this example. You're comparing the average call time between the day shift and the night shift at an inbound call center for an electronics manufacturer. You suspect that the average call time for the two shifts is equal. A random sample of 16 call times is taken from the day shift, shift 1, and 12 call times are sampled from the night shift, shift 2, to validate the hypothesis. You want to test the null hypothesis that the average call length in both the shifts is equal. The populations are assumed to be normally distributed and the samples are independent. The population variance for each shift is unknown, but it's believed to be unequal. You determine that this is a two-tailed test and set alpha at 0.05. Using this information, you can then choose the two-sample t-test for means non-pooled formula as the most suitable choice. Accordingly, then, you calculate the degrees of freedom using the two-sample t-test for means non-pooled df formula. You use the sample data to calculate the mean and standard deviation for each sample and insert the standard deviations into the formula for df. The result is 25.9. Because you always round down the df to the most conservative value, you round your answer here to 25. Then you enter the mean, standard deviation, and sample size values for each sample into the non-pooled t formula. The result is a test statistic of -1.36. You can use the df of 25 and alpha of 0.05 to reference the t-distribution table and find the critical value of 1.708. As the test statistic value of -1.36 is less than the critical value of 1.708, you fail to reject the null hypothesis. Therefore, the null hypothesis that the two shifts have equal average call duration should not be rejected. If you choose to use the p-value method, your statistical software will enable you to skip the step of calculating the t-statistic and degrees of freedom. It would account for these in the final p-value output of 0.18, which you would simply compare to the alpha value of 0.05. Regardless of the method, the final conclusion is the same. At a 0.05 alpha, the data indicates that the average call durations of the day shift and night shift are statistically similar, and the minor differences that appear in the samples are just a matter of natural variation and are not statistically significant. A two-sample test for means compares two means to determine whether or not there are significant differences between them. As with the one-sample test for means, you can follow the 5 hypothesis testing steps to complete a two-sample test. The steps are to define the business problem, establish the hypotheses, determine test parameters, calculate the test statistic, and finally, interpret the results. If the sample size is large, or population variances are known, you use a z-test. And when population variances are unknown and sample size is less than 30, you use a t-test. This is further broken down into two formulas, pooled and non-pooled. The two-sample test for means pooled formula is used when population variances are considered to be equal. The non-pooled formula is used when population variances are considered to be. One of the tools used in the analyze phase is hypothesis testing. When you're addressing a problem, it's important to validate any assumptions and hypotheses you may hold about the problem and its potential solution. Conducting hypothesis tests enables you to do this. Hypothesis testing may be useful in a variety of business situations. Do two cleaning products used to clean the same proportion of the same building perform the same or differently? Has the proportion of people over 50 who purchase a particular journal changed over time? Do two customer support centers resolve the same number of trouble tickets each day? Various types of hypothesis tests are available, and the one you will use depends on the values you wish to compare and the characteristics of the test. The 3 types of values you can test are means, proportions, and variances. Hypothesis tests have 3 main applications. One is comparing the mean, variance, or proportion of a single population to a specified value. You might use it when you need to find out whether one of these values for a population is significantly different from some fixed external measure or target. Such a target is typically a specification limit or performance goal. The second application of a hypothesis test is comparing the means, variances, or proportions of two populations. You might use it when you need to find out whether two different populations of interest are significantly different from each other. And a third application of a hypothesis test is comparing the means of 3 or more populations by using analysis of variance, or ANOVA. ANOVA will be covered in detail in the next video. From your Greenbelt studies, you should already be familiar with the key concepts of hypothesis testing. Basic concepts include the null hypothesis and the alternative hypothesis, one-tailed and two-tailed tests, and the test statistic. Other key concepts are the p-value method and the critical value method, confidence levels, type 1 and type 2 errors of statistical tests, and statistical and practical significance. You've also learned that whatever hypothesis test you choose to conduct, the steps in the testing process are the same. As with other testing processes, you must determine what you want the test to tell you, specify how the test will give you this information, gather the data, analyze the results, and reach a conclusion based on your analysis. Access the content in Key Concepts in Hypothesis Testing and the content in The Process of Hypothesis Testing after this video to review the hypothesis testing concepts and the hypothesis testing process. When would you conduct a hypothesis test for proportions? When you need to find out whether a population's proportion is significantly different from a specified value or target, or from other populations. In general, tests for proportions might tell you something about the ratio of defective items to non-defective items. To conduct a hypothesis test for proportions, you must fulfill some basic conditions. One condition is that the data must be discrete and binary. Another is that the samples must be random. The next condition is that trials must be random. A final condition is that proportions of interest must be constant. You can use hypothesis tests for proportions in two ways. First, you can compare a one-sample proportion to a specific value, such as a target or a specification. Comparing a one-sample proportion to a specific value would answer the question, is the proportion of defectives in a particular process within prescribed limits, above a prescribed limit, or below a prescribed limit? Second, you can use the test to compare two sample proportions to determine if a proportion from one sample is statistically different from another sample. Comparing two sample proportions would answer questions such as, are these significantly different? And what is the proportion of defective products before and after an improvement was made to a process? Comparison of more than two proportions is done using the chi-square statistic, which is beyond the scope of this video. Hypothesis testing for proportions can benefit your organization in a number of ways. One-sample tests can help the organization focus on urgent areas that require attention by determining whether the proportion of defectives deviates from an expected, historical, or required value in a way that could be problematic. Two-sample tests can help the organization avoid unnecessary process improvement costs by determining which improvement has the most impact on the proportion of defectives. In tests for proportions, the sample sizes should be reasonably large so that the normal distribution accurately represents the results. You should use the normal approximation method, or z-test, if the smaller of the expected number of defectives and non-defectives in the sample is greater than or equal to 5. When using the normal approximation formula, the minimum of n times p subscript 0 and n times the result of 1 minus p subscript 0 should be greater than or equal to 5, where n is the sample size and p subscript 0 is the hypothesized or expected proportion. For example, if p subscript 0 is 0.1, then n should be at least 50. Similarly, if p subscript 0 is 0.01, then n should be at least 500. In conducting a one-sample test for population proportions, you follow the basic 5 steps for hypothesis testing, just as you would in tests for means and tests for variances. The first step is to define the business problem. Consider this situation. The director of the Consumer Loans Department at a retail bank claims that over 75% of the applications for auto loans are processed within 9 business days. However, the process improvement team thinks that much less than 75% of applications are processed within 9 business days in the current loan processing system. The business problem in this case is the proportion of loan applications processed within the prescribed time limit above, equal to, or below 75%? This calls for a one-sample hypothesis test, which is used to find out if the proportion of a particular process or product is within prescribed limits. To test the hypothesis with 95% confidence that the current proportion of applications processed within the accepted time frame is different from that claimed by the director, the team first records 25 samples of processing times and presents them in a table. The team members test the assumption that the sample data is normally distributed, random and independent, with constant variance. They find that n times p subscript 0 is equal to 25 times 0.75, or 18.75, and that n times the result of 1 minus p subscript 0 is equal to 25 times 0.25, or 6.25. Since both values are greater than or equal to 5, the team's assumptions are met. Next, the team must establish the hypotheses. In this case, the hypothesized proportion P0 is 75 divided by 100, or 0.75. Let's consider how the null hypothesis and alternative hypothesis are established. The null hypothesis, H0, is that the population proportion, P, is greater than or equal to the hypothesized proportion, in this case 0.75. And the alternative hypothesis, HA, is that the population proportion is less than the hypothesized proportion, 0.75. The third step in the process is to determine the test parameters. This will be a one-tailed test, as the alternative hypothesis includes a less than sign. An alpha value of 0.05 places the confidence level at 95%. Also, the critical value method is applied in this test. The fourth step is to calculate the test statistic for the test, using the formula for a one-sample proportion test. Let's consider each parameter and its value. The character P is the population proportion, and the character N is the sample size. In this case, the value is 25. The character X is the number of items in the sample with the defined attribute. In this case, the value is 16. And the character P' is the sample proportion, or X divided by N. In this case, the value is 16 divided by 25, or 0.64. And last, the character P0 is the hypothesized proportion. In this case, the value is 0.75. Given the P subscript 0 and P' values of 0.75 and 0.64 respectively, the N value of 25, and the X value of 16, the test statistic Z is calculated using the formula, and the result is -1.27. However, please note that an absolute value of the test statistic is used in hypothesis testing, so the test statistic is 1.27. When determining significance in tests for proportions, you can use two methods. All tests for proportions, as well as for means and variances, use either the critical value method or the p-value method for determining significance. To use the critical value method, you need to calculate the critical value for the given alpha value and degrees of freedom in step 3 of the process. Then, when interpreting the results of the test, you compare the test statistic outcome with the critical value to reject or fail to reject the null hypothesis. When the test statistic value is greater than the critical value, you reject the null hypothesis. When the test statistic value is less than the critical value, you fail to reject the null hypothesis. The p-value method is a popular choice among Six Sigma practitioners, as many software programs give results in terms of the p-value. To use this method, you need to determine the p-value for a test statistic in the final step of the testing process. You can find this value using a table. The p-value is then compared with the alpha value and, based on this comparison, you fail to reject a null hypothesis when the p-value is greater than the alpha value, usually 0.05, and reject a null hypothesis when the p-value is less than the alpha value. Using the Z critical value lookup table, the team finds that the critical value for alpha, or 0.05, in a one-tailed test is calculated as 1.645. The final step is to interpret the results of the test. As the test statistic value is less than the critical value, the test fails to reject the null hypothesis. In other words, the claim made by the director of the Consumer Loans Department, that the current loan processing time is less than 9 days in more than 75% of cases, is validated by the test, with a 95% confidence level. You can access the job aid test statistic formulas after this video as a reference for all of the tests for proportion and variance. In comparison to one-sample tests for proportions, the two-sample test for proportions allows you to compare two data populations. Instead of using a target value for comparison, the two-sample test compares sample proportions from two populations. This makes it useful for comparing two processes, for example, a pre-improvement process and a post-improvement process. An example of a two-sample test for proportions is where a team needs to compare two samples to find out if they are significantly different. Suppose you are part of a Six Sigma team that is analyzing the call durations of the day and night shifts at an inbound international call center. Your goal is to determine whether there is a significant difference between the proportion of escalated calls in the two shifts. For this test, the team takes 400 random samples of all inbound calls from the day shift and 300 from the night shift. Of these samples, 25 were escalated to the next tier of support in the day shift, and 42 were escalated in the night shift. The team confirms that the population data for each shift is normally distributed and that it is independent, random, and with constant variance. The team now needs to determine if it can be inferred from the samples that, on the whole, the escalations for both the shifts are different. Next, you and your team establish the hypotheses. The null hypothesis states that the population proportions for the two shifts are equal. In other words, that the proportion of escalations are the same for each shift. And the alternative hypothesis is that the population proportions for the two shifts are not equal. The team determines the test parameters. They assume a confidence level of 95%. They also determine that this is a two-tailed test, as the alternative hypothesis includes an inequality sign. And the method used for this test is the p-value method. The team calculates the test statistic using the formula for two sample tests for proportions. The formula element P'1 is the sample proportion for the day shift. In this case, the value is 25 divided by 400, or 0.0625. And P'2 is the sample proportion for the night shift. In this case, the value is 42 divided by 300, or 0.140. The formula element X subscript 1 represents the number of items in the day shift sample with the defined attribute, in this case, 25. And X subscript 2 represents the number of items in the night shift sample with the defined attribute, in this case, 42. In this case, N subscript 1 represents the sample size for the day shift, 400, and N subscript 2 represents the sample size for the night shift, 300. And the mathematical expression P' subscript P is calculated by dividing the sum of X subscript 1 and X subscript 2 by the sum of N subscript 1 and N subscript 2. Calculating the z-test statistic with the given values, the team calculates z as 3.50. Using the table, the team finds the p-value, which is 0.0002. Finally, the team interprets the results. As the p-value is less than alpha, the null hypothesis is rejected. In other words, the proportions of escalation of the day and night shift are not equal. This means that the proportion of escalated cases in the day shift is significantly different from that of the night shift. In practical terms, there is something other than mere chance at play in this difference, and the Six Sigma team needs to investigate. Hypothesis testing allows you to validate any assumptions and hypotheses you may hold about a problem and its potential solution. You can use hypothesis tests to test proportions, means, and variances. All hypothesis tests follow the same 5-step process. Identify the business problem, establish the hypotheses, determine the test parameters, calculate the test statistic, and interpret the results. Hypothesis tests for proportions allow you to find out whether a population's proportion is significantly different from a specified value or target. You can compare a one-sample proportion to a specific value, or compare two sample proportions to determine whether a proportion from one sample is statistically different from another sample. In tests for proportions, the sample sizes should be reasonably large so that the normal distribution accurately represents the results. When performing hypothesis tests, the population's variance, or standard deviation, is often of greater significance than the population mean. It can be crucial to confirm that the observed variance of a population is actually at the value that you expect or require. For example, the population variance will be significant for a tire manufacturer that wants to develop a new type of tire with a more consistent overall wear rate. The variation of wear in the new tire must be smaller than the variation in the tire currently being manufactured. Similarly, the population variance will be significant for a manufacturer of automobile speedometers that wants to compare measurement precision among several speed gauges. To compare the variance in a single population with a specified value, you use a one-sample test for variance. All tests for variance follow the usual 5-step process for hypothesis testing. In most one-sample hypothesis tests for variance, the null hypothesis is that there is no difference, and the alternative hypothesis is that variance is either not equal to, greater than, or less than the specified value. In a population with a normal distribution, The null hypothesis for comparing a population variance, small sigma squared x, with a fixed value, small sigma squared 0, is that the variances are equal. And the alternative hypothesis is that the variances are not equal. Where the null hypothesis is rejected in favor of the alternative hypothesis, the team needs to go back and investigate the process. Consider an example. You are investigating the variance of a box filling machine in a cereal manufacturing plant. The machine is centered to operate at 15 ounces, but is showing a high level of variability. The variance of this machine should be 1.8 ounces, so you run a test to find out if the variance of the machine is greater than 1.8 ounces squared. The null hypothesis states that the variance of the machine is equal to 1.8. And the alternative hypothesis states that the variance of the machine is greater than 1.8. What are the unique features of one-sample tests for variances? You need to consider 4 key areas. First is the test statistic. The chi-square test statistic is used to test whether the variance of a population is equal to a specified value. This test uses the chi-square distribution. A second key feature of one-sample variance test is critical value. Chi-square tables differ for right-tailed and left-tailed tests, which must be considered when looking up the critical value. Another feature is the degrees of freedom of a statistic. This is the number of parameters, which may be independently varied. And finally, data must be continuous, independent, randomly sampled, and normally distributed. Suppose that you are the manager of a parts manufacturing facility. A process has been running for some time with a variance of 6.25 for a critical dimension. To improve throughput, an engineer increases the speed of the drive motor. From the new process, 33 samples are randomly selected, and the variance for these samples is shown to be 6.76. The first step of the hypothesis testing process is to define the business problem. In this case, whether the variance has increased. Because you need to compare a variance with a historical value of 6.25, you choose to conduct a one-sample test for variance. The second step is to establish the hypotheses. In one-sample tests for variance, the null hypothesis is typically that there is no significant difference between the population variance, estimated based on samples, and the specified value, whereas the alternative hypothesis is that there is a significant difference. You establish these hypotheses. The null hypothesis is that the population variance is equal to 6.25, and the alternative hypothesis is that the population variance is greater than 6.25. The third step is to determine the test parameters. First, the distribution must be determined. One-sample tests for variance use the chi-square distribution. It should also be determined whether the test should be one-tailed or two-tailed. The test should be one-tailed for the right-hand tail because the alternative hypothesis includes the greater than value. The alpha or significance level should also be determined. This is the probability that the null hypothesis will be rejected. The alpha value is typically set at 0.05. A final parameter that needs to be determined is degrees of freedom. You calculate the degrees of freedom, or DF, using n-1, where n is the sample size. In this case, the degrees of freedom value is calculated as 32. The chi-square distribution, used in one-sample variance tests, is not symmetric but skewed to the right. It is highly skewed for small degrees of freedom, but becomes more and more symmetric as the degrees of freedom increase. It must also be assumed that the data is continuous, independent, and randomly sampled. The fourth step is to calculate the test statistic using the chi-square formula. Because chi-square tests are sensitive to normality, you should submit the data to a test for normality before testing for variance. Let's consider each element of the test statistic. The value s squared is the sample variance, in this case 6.76, and the value of n-1 is the degrees of freedom, in this case 33-1, or 32. And lastly, the value sigma squared 0 is the specified variance, in this case 6.25. So, the result of the test statistic calculation is 34.61. The team must determine the significance of this value using either the p-value method or the critical value method. Both methods are equally valid, but the p-value method is more popular because it's the value that many statistical software programs return. Access the content in Test Statistic Formulas after this video to use as a reference when calculating degrees of freedom and other values in tests for variance. Because of the lack of symmetry of the chi-square distribution, chi-square critical values differ for right-tailed tests and left-tailed tests. You need to ensure that you are looking in the correct table for your value. For a right-tailed test, find the value in the table corresponding to alpha and the relevant df and reject the null hypothesis if the test statistic is greater than the tabled value. For a left-tailed test, find the value in the table corresponding to 1 minus alpha and reject the null hypothesis if the test statistic is less than the tabled value. If your alternative hypothesis contains not equal to a two-tailed test, find the critical value in the table corresponding to alpha divided by 2 and reject the null hypothesis if the test statistic is greater than the tabled value. Similarly, find the critical value corresponding to 1 minus alpha divided by 2 and reject the null hypothesis if the test statistic is less than the tabled value. The final step is to interpret the results. By finding the critical value on a chi-square table and knowing the test statistic, which in this example is 34.61, you can determine if the null hypothesis is rejected. Recall that the null hypothesis is rejected if the test statistic is greater than the critical value. You can access the job aid chi-square tables after this video to find critical values for one-sample tests for variance. The one-sample test for variance can benefit an organization in two ways. First, it can let a team know that a process's variation is within an expected range and therefore not in need of improvement. And second, it can let the team know that a process's variation is not within a required range, therefore targeting the process for improvement. If you wish to determine which of two samples exhibits the largest variance, you use a two-sample test for variance. The population samples for this test may come from two different processes or from the same process at two different times, for example, before and after an improvement initiative. For example, you may have two processes that are perfectly centered, but a comparison of the variances can tell you if either process is better. In a two-sample test for variance, you use the F-test to compare the variances between two populations. The F-distribution is used to plot the ratio of two variances. For the F-test to be used as a test statistic, the data must be normally distributed, as well as independent, randomly sampled, and continuous. Access the content Performing a Test for Variance after this video to review the steps involved in performing a two-sample hypothesis test for variance. Consider this example. You are part of a Six Sigma team in a paper factory that is comparing the output of two machines built to extract water from wood pulp. Your team finds that the two machines exhibit different variances in the extracted water quantities. Machine 1 is found to have a variance of 6.7, and Machine 2 is found to have a variance of 2.5. The first step of the hypothesis testing process is to define the business problem. The team defines this as, which method shows the greater variance? You collect data from 25 outputs for each of Machine 1 and Machine 2. This is a two-sample test because you want to compare differences in variance between two sample populations. The second step is to establish the hypotheses. The null hypothesis is that the two variances are equal, and the alternative hypothesis is that the variance for population 2 is smaller than the variance for population 1. The third step is to determine the test parameters. The team assumes a confidence level of 0.05 for the test. Using an F-table, the team finds a critical value of 1.98. The fourth step is to calculate the test statistic using the F-test formula. This formula calculates the F-test statistic by dividing the variance of the larger sample, S squared subscript 1, by the variance of the smaller sample, S squared subscript 2. So Machine 1 produced a sample variance of 6.7, and Machine 2 produced a sample variance of 2.5. The final step is to interpret the results. The value of the test statistic, 2.68, is greater than the cutoff value of 1.98, so the team rejects the null hypothesis. It's concluded that the variability of machine 1 is greater than the variability of machine 2. To determine significance, you can compare the F statistic to the critical value in a table, or you can calculate the p-value, which is typically done using statistical software. Using the p-value method, you find that the p-value is less than the confidence level set. This means that the null hypothesis is rejected. Conducting a two-sample test for variances can have a number of benefits for your organization. First, rejecting a null hypothesis may indicate that an improvement project made a significant difference in the variance of a process. It can also justify the quality of an organization's product by comparing the variance in product characteristics with that of a leading competitor. And failing to reject a null hypothesis may save your organization money when it's discovered that a cheaper solution has lesser or similar variability compared to a more expensive solution. It can also help you to make decisions about changing suppliers. For example, if you find that the variability in the delivery time of a new supplier is no different from that of your existing supplier. When performing hypothesis tests, the population's variance, or standard deviation, is often of greater significance than the population mean. To compare the variance in a single population with a specified value, you use a one-sample test for variance. In most one-sample tests, the null hypothesis is that there is no difference, and the alternative hypothesis is that variance is either not equal to, more than, or less than the specified value. You use the chi-square test statistic in one-sample tests. If you wish to determine which of two samples exhibits the largest variance, you use a two-sample test for variance. This test uses the F-test to compare the variances between two Hypothesis tests, such as z-tests and t-tests, are useful for testing the values of a single population mean or the difference between two means. But sometimes it's necessary to compare 3 or more population means simultaneously. Suppose you want to compare how 3 different temperature settings affect the moisture content of a product to determine if there is a significant difference between them. If there is, you want to find out which one results in the least amount of moisture. So, how do you compare 3 population means? ANOVA, or Analysis of Variance, is a special application of the two-sample t-test for means that allows you to compare the means of 3 or more populations. So, to perform a hypothesis test to find out whether 3 levels of temperature significantly affect the moisture content of a product, you use ANOVA instead of the two-sample t-test. ANOVA can be applied to any number of datasets recorded from any process using statistical software packages. It uses samples from each dataset to test the null hypothesis that all population means are equal. In one-way ANOVA, or single-factor ANOVA, the total variation in the data consists of 2 parts, the variation among treatment means and the variation within treatments, or experimental error. And in two-way ANOVA, or two-factor ANOVA, there are 3 components of variance: factor A treatments, factor B treatments, and experimental error. When using ANOVA, you need to consider 3 key concepts. First is the factor. A factor is a categorical variable, which means that it classifies people, objects, or events. For example, you might classify the supplier of a particular part as a factor or possible cause of variation in the performance of a machine. There is only one factor in one-way ANOVA. Another key concept is level. A level is a group within the factor. For example, you might have 5 suppliers you wish to test. In this case, the factor has 5 levels. Response is the third key concept to consider when using ANOVA. Response is the variable you are interested in testing, for example, the performance of a machine. It's important to distinguish between within-group variation and between-group variation. Within-group variation, or experimental error, occurs when there is variability between measurements within a single group or factor level. In one-way ANOVA, this is always assumed to be due to experimental error. On the other hand, between-group variation occurs when there is variability in measurements between all groups. ANOVA compares between-group variation to within-group variation to determine whether there are significant differences in means between groups. Consider this example. A Six Sigma team at a manufacturer of rock climbing equipment must choose 1 out of 4 possible nylon material suppliers to produce the company's climbing harnesses. The decision will be based on which supplier provides the material of greatest tensile strength. The team tests a random sample of material from each supplier by stretching the material to its breaking point. The results are plotted on a graph within and between the groups. The test finds a wide variation between strength measurements across the 4 suppliers. If this between-group variation is large relative to the within-group variation, this suggests that the population means are different. In addition, the test finds a wide variation in tensile strength between the material samples within each supplier group. In ANOVA, this within-group variation is assumed to be due to experimental error. To recap, the null hypothesis in ANOVA states that the population means of all datasets are equal. ANOVA allows you to determine whether the ratio of the between-group variation to the within-group variation is large enough to reject the null hypothesis with a desired level of confidence. The 2 variations are compared using the F-statistic. The F-statistic uses the 2 variance values in ANOVA to calculate a ratio of variance. The numerator, between-group variance, is the sum of factor-related variance between treatment groups, and the denominator, within-group variance, is the sum of error-related variance within treatment groups. Calculating the F-statistic, that is, the ratio of between-group variation to within-group variation, will allow you to determine whether the between-treatment variation is a large enough multiple of the within-treatment variation to be statistically significant. Returning to the rock climbing harness example, the testers find that there's a large amount of variation in the strength of material among the 4 suppliers. There's also some within-group variation. The degree of relative difference between them will tell you whether the means are the same or not. The ratio is equal to F. Like other hypothesis tests, ANOVA aligns with the standard 5-step procedure for hypothesis testing. As a greenbelt, you should already be familiar with this procedure, as well as the key concepts and terminology of ANOVA. Access the content Single-Factor ANOVA after this video if you wish to review key concepts of ANOVA. Consider this scenario, which illustrates the 5-step hypothesis procedure. Automobile insurance claims at a large insurance company are processed at 5 centers spread across North America. A process improvement project has been initiated to determine if the average claim processing time is the same at all processing centers. 7 observations are randomly sampled from each processing center, and the results are tabulated. The first step in conducting the hypothesis test is to define the business problem. As you define the problem, you must also verify that the 3 assumptions for ANOVA are met. You can verify the 3 assumptions using residuals analysis. A residual is the difference between the observed value and the fitted value or the group mean. Residuals are estimates of the error in ANOVA. The second step of the process is to establish the hypotheses. For one-way ANOVA, the null hypothesis is typically that the mean for each level is equal to the mean for the other levels. Let's consider the hypotheses in the claim processing example. The null hypothesis is that the population means of the processing time at all the processing centers are equal. And the alternative hypothesis is that not all the means are equal. That is, at least one mean is different. The third step is to determine the test parameters. This means setting the alpha risk value and calculating degrees of freedom for each source of variation. That is, for the numerator and denominator of the F-statistic. In this case, assume an alpha risk value of 0.05. You need to calculate the degrees of freedom at 3 levels: factor, error, and total. Let's consider how degrees of freedom, dF, are calculated for each level. The degrees of freedom between treatments, or dF factor, is calculated as the number of levels, or treatments, k minus 1. And the degrees of freedom within treatment, or DF error, is calculated as the number of readings, or n minus k. And finally, the degrees of freedom total is calculated as the number of readings, or n minus 1, or as the sum of DF factor plus DF error. In the claims processing example, the DF factor value is calculated as 5 minus 1, or 4. The DF error value is 35 minus 5, or 30. And the DF total value is the sum of DF factor and DF error, which is 34. The fourth step is to calculate the test statistic. There are several components used in ANOVA to calculate the test statistic, and these will be familiar to you from your Greenbelt studies. However, there are 4 intermediate values used in calculating the test statistic that may be new to you. One value is the value uppercase C, which is the correction factor and is calculated using the value uppercase T, the grand total of readings, and uppercase N, the total number of readings. Another value is uppercase T, or TI, which is the grand total of readings and is used in the calculation of uppercase C. SS factor is a third intermediate value, and it's the sum of squares between treatments. You can calculate SS factor using a more cumbersome summation formula, but this simpler shortcut formula makes use of the easily calculated uppercase T and uppercase C values. A fourth intermediate value is SS total. SS total is the total sum of squares and is calculated using this formula. An easier way to calculate it is by adding together SS factor and SS error. While you can calculate SS total using a summation formula, this simpler formula makes use of the easily calculated uppercase C value. You can access the job aid ANOVA values after this video to review information on the formulas used for the calculation in ANOVA. You calculate the values for the test statistic using an ANOVA table. The table consists of columns for sources of variation, sums of squares, degrees of freedom, and mean squares for both between-group and within-group variations. In the claims processing example, the team starts filling in the ANOVA table by calculating some preliminary values. They calculate that the total number of readings, or uppercase N, is 35, and the number of levels, or K, is 5, and the number of readings per level, or N, is 7. The team also calculates the grand total of readings, or uppercase T, as the sum of 72.1, 76.5, 73.1, 74.6, and 75.5, giving a total of 371.8. They also calculate the value yi squared, the squared sum of all individual measurements, and it is 3,960.7. Then the value uppercase Ti squared is calculated as 27,659.7. And the correction factor, uppercase C, is calculated as uppercase T squared divided by uppercase N, or 3,949.58. Now that the formula components have been calculated, the team can fill in the ANOVA table. The team calculated the sum of squares total, or SS total, as 3,960.70 minus 3,949.58, or 11.12. And the sum of squares between treatment, or SS factor, is 27,659.7 divided by 7 minus 3,949.58. This gives a total of 1.81. The sum of squares within treatment, or SS error, is the difference between SS total and SS factor, which is 11.12 minus 1.81, or 9.31. And the MS factor is the SS factor divided by DF factor, which is 1.81 divided by 4, or 0.45. And finally, the MS error is the SS error divided by the DF error, which is 9.31 divided by 30, or 0.31. Once the ANOVA table is filled in, the next step is to interpret the results. As with all hypothesis tests, such as the t-test, you have two choices for validating the results. The critical value method, which involves looking up the critical value on an F-table, or the p-value method, which involves calculating the p-value for the F statistic and comparing it to the alpha risk value. Most statistical packages use the p-value method. You can also determine this value using a table. Now, return to the claims processing scenario. You decide to use the critical value method. To do this, you consult the F-statistic table containing critical values for a 0.05 alpha value. In the table, there are values for different numerator degrees of freedom and denominator degrees of freedom. You find the value for your numerator value of 4 and denominator value of 30. This value is 2.69. You can access the job aid Critical Values for F Distribution after this video to help you find critical values based on the F distribution and the 0.05 alpha value. The F statistic was previously calculated as 1.45. This is less than the critical value, 2.69, so the null hypothesis cannot be rejected and is thus retained. As an alternative, you could use the p-value method. To do this, you can use any online p-value calculator. For the F statistic of 1.45, the p-value is calculated as 0.241, which is more than the alpha risk value of 0.05. This means that the null hypothesis is retained, just as it was by the critical value procedure. The results of the test can be expressed as follows. Since the null hypothesis is retained, it can be inferred that the average processing times at the 5 centers are equal. There is no statistically significant difference between the average processing times at the 5 centers, and the difference that appears in the samples might be just due to chance. While ANOVA helps to determine whether the population means for all levels are equal, you can also use some advanced tools to identify which means are different from the rest. This knowledge can help you make decisions, such as which supplier to retain in order to maximize the quality of your final product. A full discussion of these tools is beyond the scope of this course. ANOVA, or Analysis of Variance, is a special application of the two-sample t-test for means. It allows you to compare the means of 2 or more populations. In one-way ANOVA, or single-factor ANOVA, the total variation in the data consists of the variation among treatment means and the variation within treatments. Variation within treatments is assumed by ANOVA to be due to experimental error. Like other hypothesis tests, ANOVA uses the 5-step hypothesis testing procedure. ANOVA determines whether the ratio of the between-group variation to the within-group variation is large enough to reject the null hypothesis with a desired level of confidence. The two variations are compared using the F statistic. Degrees of freedom must be calculated for each source of variation, and the test statistic is calculated using an ANOVA table. The test result can be validated using either the critical value method or the p-value method. It's one thing to analyze the effects of single factors or variables, but how do you analyze factors that, when occurring together, have an effect on each other? Just as in chemical processes, each factor has a specific effect on its own, but may produce a completely different effect when it's mixed with another factor. Two-way ANOVA, also known as two-factor ANOVA, is the analysis of two-factor factorial experiments. It's used to investigate differences among population means when 2 or more factors are involved. In two-way ANOVA, there are 4 areas of interest. One area of interest is the effect of factor A on variance. The effect of factor B on variance is another area of interest. Third is the effect of the interaction of factor A and factor B on variance. And the fourth area of interest in two-way ANOVA is the within-treatment variance. Consider this example. A manufacturer of cleaning products makes 2 different types of cleaner, original and unscented. An employee notices that the measurement nozzles on the bottles for each type dispense slightly different amounts. Each nozzle should dispense the same amount, so the employee decides to run a test that uses a regular nozzle type and a modified nozzle type for each product. This test has 2 factors, product type and nozzle type. The test can't use one-way ANOVA because one-way ANOVA examines differences in means of only one factor. Instead, the test must use two-way ANOVA. Let's take a look at how each area of interest relates to the cleaning product variance example. The first factor, factor A, is the nozzle type, regular or modified. The second factor, factor B, is the type of cleaning product, original or unscented. In addition to testing the main effect of each factor, you must take into account any interaction between the factors, that is, whether they have any effect on each other. For example, does the amount dispensed by the nozzle depend on the product? And finally, the within-treatment variance is assumed to be due to experimental error in two-way ANOVA. So there are two levels for each factor in the example. For factor A, nozzle type, the levels are the current and modified nozzle types. The levels for factor B, product type, are the original and unscented formulas. The procedure for two-way ANOVA is very similar to that for one-way ANOVA. Both follow the typical 5-step procedure for hypothesis testing: define the business problem, establish the hypotheses, determine the test parameters, calculate the test statistic, and interpret the results. And two-way ANOVA maintains the same 3 assumptions about the data as one-way ANOVA. One assumption is that samples are random and independent. Another assumption is that the population is normally distributed. And the third assumption is that variances are constant. In the cleaning product measurement example, the business problem is defined as whether the variance in the amount of product dispensed is affected by the type of product, the type of nozzle, or the interaction of both. The second step is to establish the null and alternative hypotheses. For the two-way ANOVA, the possible null hypotheses are that there is no difference in the mean response across levels for nozzle type, factor A. There is no difference in the mean response across levels for cleaning product type, factor B. And there is no interaction between nozzle type and cleaning product type, factors A and B. And the alternative hypothesis is that there is a difference in the mean response across levels for nozzle type, there is a difference in the mean response across levels for cleaning product type, and there is an interaction between nozzle type and cleaning product type. As with one-way ANOVA, you use the F statistic to calculate the ratio of between-group variation to within-group variation. If the between-group variation is small compared to the within-group variation, this suggests that there is no significant difference between the population means. But if the ratio is large, then the population means are different. In the cleaning product example, the F statistic suggests that there is a significant difference. In the third step, determining the test parameters, an alpha risk value of 0.05 is assumed. The degrees of freedom, df, for each factor is calculated as the number of levels minus 1, giving a df of 1 for each factor. The df for the interaction will be equal to the value found by multiplying the df for each factor. The df for error is calculated by multiplying the number of levels for the factors and subtracting the result from the total number of readings. When calculating the test statistic, you use all the same components that are used in one-way ANOVA. However, many of the components have A and B variance for each factor. For example, you use only one value, K, to signify the number of levels or treatments for the factor in one-way ANOVA. But in two-way ANOVA, you need 2 such values, N subscript A and N subscript B. In two-way ANOVA, N represents the total number of readings. Unlike one-way ANOVA, two-way ANOVA deals with 4 sources of variation, all of which must be included in the ANOVA table. The 4 sources are factor A, factor B, the interaction between the factors, and the experimental error. In two-way ANOVA, you perform 3 calculations. One calculation is to find the sum of squares, the mean square, and the F statistic for factor A. Another calculation is to find the sum of squares, the mean square, and the F statistic for factor B. A third calculation is to find the sum of squares, the mean square, and the F statistic for the interaction between factor A and factor B. Let's consider how each component of the ANOVA table relates to the cleaning product measurement test. For factor A, you calculate the sum of squares as 0.0000795, the mean square as 0.0000795, and the F statistic as 6.36. For factor B, You calculate the sum of squares as 0.0004007, the mean square as 0.0004007, and the f-statistic as 32.07. And for the interaction between the factors, you calculate the sum of squares as 0.0000504, the mean square as 0.0000504, and the f-statistic as 4.03. The two-way ANOVA table thus gives you information about main effects and interaction of factors. But in order to reject or fail to reject the null hypotheses, you need to test for each main effect and interaction. To interpret the results of the test, you find the p-values for the f-statistics calculated in the ANOVA table. The f-statistic for factor A is 6.36, it's 32.07 for factor B, and for the interaction between both factors, it's 4.03. And the p-value for the f-statistic for factor A is 0.013. It's 0 for factor B, and for the interaction between both factors, it's 0.046. In two-way ANOVA, you must test whether main effects of factors and their interactions are statistically significant. If the p-value is greater than the alpha risk value, you fail to reject the null hypotheses. Since in the cleaning product measurement test, the p-values for main effects and interactions are less than the alpha value of 0.05, the null hypotheses are rejected in favor of the alternative hypothesis. So, based on the results of this test, it can be said with 95% confidence that the variation in the mean response among volumes of cleaning product dispensed by each nozzle is affected by both of the factors, nozzle type and cleaning product type, and also by their interaction. Two-way ANOVA, also known as two-factor ANOVA, is the analysis of two-factor factorial experiments. It's used to investigate differences among population means when more than two factors are involved. The four areas of interest in a two-way ANOVA are the effect of factor A on variance, the effect of factor B on variance, the effect of the interaction of factor A and factor B on variance, and the experimental error. The test procedure and assumptions for two-way ANOVA are similar to those used for one-way ANOVA, except that components have an A and a B variant corresponding to factor A and factor B. Also, you perform an additional calculation for the interaction of the two. How can you determine whether the distribution of defects in your product or service has changed from the historic distribution over time or exceeds an industry standard? In such cases, variance is a more significant variable than mean. Comparing a population's variance to a standard value involves calculating the chi-square test statistic. Other problems requiring the chi-square test statistic include determining whether one variable is dependent upon another, or comparing observed and expected frequencies where the variance is unknown. The chi-square test statistic is a versatile tool. You can even use it to compare multiple proportions, but that is beyond the scope of this course. Let's consider each hypothesis testing situation to learn more about different uses of the chi-square test statistic in Six Sigma. First, to compare variance to a standard value, you use a one-sample test for variance. This test uses a version of the chi-square test statistic. And to determine whether one variable is dependent upon another variable, you use a contingency table along with the chi-square test statistic. This will be dealt with in the next video of the course. And finally, you can use the chi-square test statistic to compare observed frequencies with expected frequencies of a population with unknown variance. This version of a chi-square test is better known as a goodness of fit test, which is the term that will be used in this video. Goodness of fit tests are the focus of this video. They employ the chi-square test statistic and share some other similarities with contingency tables, which also compare observed and expected frequencies. But contingency tables and goodness of fit tests differ in their goals, hypotheses, and interpretations. A contingency table is a table of frequencies classified according to the values of the variables. It summarizes the relationship or interaction between the variables to assess whether or not the contents of the rows are contingent or dependent upon, the contents of the columns. The goal of goodness of fit tests is to test assumptions about the distributions that fit the process data. Essentially, a goodness of fit test asks if the observed frequencies, O, are the same or different from the historical, expected, or theoretical frequencies, E. If there's a difference between them, this suggests that the distribution model expressed by the expected frequencies does not fit the data. Goodness of fit tests can be structured in table cells. In one column of the table, each cell contains an observed frequency, FO or O. Depending on the nature of the problem, the theoretical or expected frequency, FE or E, is already known or can be calculated. You then use the chi-square formula to calculate and sum the chi-square statistic across all cells. Observed frequencies are the frequencies actually obtained from the sample data in the table, and expected frequencies are the frequencies you would expect in each cell of the table if you knew only the row and column totals, and if you assumed that the variables being compared were independent. As a Six Sigma Black Belt, you'll often encounter business problems that require a goodness of fit test. Such problems require you to compare the observed frequencies of test outcomes with the expected frequencies. Let's consider some examples to learn about business problems that require a goodness of fit test. Suppose a finished pharmaceutical product shows a varying distribution of defectives both before and after an improvement process. The manager wants to know if the distribution of defectives is different post-improvement. A goodness of fit test can compare the observed frequencies, the data from the tests, to the expected frequencies, the distribution of defectives before the improvement took place. A second example is a manufacturer of heart monitoring equipment that wants to compare the measurement precision among several instruments based on historical values. A goodness of fit test enables a comparison between observed and expected frequencies, or the historical values and the values observed in the tests. And a final example, a hospital suspects there is an unusual distribution of blood types in patients undergoing a particular surgical procedure, compared to the expected distribution for the population served by the hospital. A goodness of fit test is conducted to find out if the population distribution, the observed frequency, is different from the overall distribution for the region, the expected frequency. When performing a goodness of fit test, your goal is to test whether the observed frequency fits the expected frequency. If it doesn't, you may need to revisit your model of expected frequencies. Consider this scenario. You're working on improving a financial lending institution's customer service. A customer satisfaction survey's results for the past 2 years have been 20% excellent, 40% good, 30% fair, and 10% poor. Following improvements to the customer service process, new data from a survey of 600 customers gave the following results: 150 excellent, 290 good, 140 fair, and 20 poor. You want to determine whether the distribution of the new results differs from the historical results. To conduct this hypothesis test, you follow the 5-step process used for all hypothesis tests. In the first step, the business problem or organizational question is, do the results from the new survey mean that the company's customer satisfaction performance has changed? Then you establish the null and alternative hypotheses. The null hypothesis is that the distribution of the new results is the same as the distribution of the historical or expected results across the 4 levels: excellent, good, fair, and poor. And the alternative hypothesis is that at least one value under the 4 levels is different from the historical values specified in the null hypothesis. You usually calculate the degrees of freedom for chi-square as n-1. However, in some cases, you may wish to establish whether the data fits a specific distribution, such as binomial or Poisson, by performing more advanced goodness of fit tests. If you do, you'll need more precise calculations of degrees of freedom. However, since you're conducting a normal goodness of fit test, you calculate the degrees of freedom as n-1, where n is the number of levels. Since there are 4 levels in the test, this gives 4 minus 1, or 3. The alpha value for this test is 0.05. To determine the test statistic for a test comparing observed frequencies with expected frequencies, you use the chi-square test statistic formula. When performing the calculations for this formula manually, it's helpful to put the values in a table with the rows representing the different levels, excellent, good, fair, and poor, and the columns representing the observed and expected values. You begin by entering the observed frequencies, or the results of the new customer survey. Next, you enter the expected frequencies, or E, for each level. You calculate these by multiplying the expected value by 600, which is the number of customers polled in the new survey, by the expected proportions. For example, for the excellent level, the expected frequency is 600 multiplied by 0.20, or 120. Next, you calculate the squared difference between O and E and divide by E for each level. Let's consider how each value in the final column was calculated. To calculate the squared difference between O and E divided by E for the excellent level, you square the difference between 150 and 120 and then divide this by 120, which gives you 7.5. And to calculate the squared difference between O and E divided by E for the good level, you square the difference between 290 and 240, then divide this by 240, which gives you 10.42. And finally, to calculate the squared difference between O and E divided by E for the fair level, you square the difference between 140 and 180, then divide this by 180, which gives you 8.89. For this calculation, the O value is larger than the E value, so subtracting them gives a negative number. However, when you square this number, it changes to a positive value. To complete the calculation of the chi-square test statistic for the table, you sum all the values that you obtained using the chi-square test statistic formula in each cell of the square difference between O and E divided by E column. This gives a total chi-square test statistic value of 53.48. The final step is to interpret the results of the test. To do this, you consult the chi-square table or a software application to compare the calculated test statistic to the associated critical value, or to compare the p-value to alpha. If the test statistic value is in the rejection region, or if the p-value is less than the value of alpha, you reject the null hypothesis. When you look up critical values in a chi-square table, the goodness of fit test is always a right-tailed test. In this case, you employ the critical value method and look up the critical value in the chi-square table. Based on an alpha value of 0.05 and 3 degrees of freedom, the critical value is 7.815. Since the test statistic value of 53.48 is greater than 7.815, and thus falls within the rejection region to the right of the table, the null hypothesis is rejected. You can access the job aid Goodness of Fit test after this video for a summary of what's involved in performing a Goodness of Fit test. Your statement of interpretation should identify 3 things about the test: the confidence level, whether or not the null hypothesis should be rejected, and whether or not a significant difference exists between observed and expected frequencies for the variable in question. Your Goodness of Fit test rejects the null hypothesis that the distribution of the new results is the same as the distribution of the historical or expected results across the 4 levels with a 95% confidence level. So, based on this study, you can conclude with 95% confidence that not all of the proportions of customer satisfaction scores are the same after the process improvement. Assessing variance typically involves applying the chi-square test statistic. Some problems require you to compare observed frequencies with expected frequencies of test outcomes when population variance is unknown. You can do this using a chi-square-based Goodness of Fit test. Goodness of Fit tests are structured in table cells, which contain observed frequencies and expected frequencies. If there's a difference between the two, this suggests that the distribution model expressed by the expected frequencies doesn't fit the data. You use the chi-square formula to calculate and sum the squared difference between O and E divided by E values across all cells. You can then compare the chi-square test statistic to a critical value or determine its associated p-value. Your interpretation of the test should specify the confidence level and whether a significant difference exists between observed and expected frequencies. It can be important to determine whether there's a relationship or dependency between two variables. For example, you may need to know whether a defect in a product is dependent on the product type or whether the two are statistically independent. Or you might want to determine whether the number of equipment breakdowns is related to the equipment operator or the number of customer complaints related to region. You can use contingency tables to determine whether a dependency exists between two variables. Contingency tables can tell you, for example, whether the distribution of defectives varies with product type. A contingency table is a two-way table consisting of rows and columns. Rows represent one variable and columns represent the other. One way to approach contingency tables is to create separate tables for each frequency type and for the square difference of observed minus expected divided by expected calculations, which are ultimately summed to determine the chi-square test statistic. The first table should hold the observed frequencies, or O, of your population. In this table, you label the rows with each category of one variable, and you label the columns with each category of the other variable. Then you calculate the proportion of the total accounted for by each row. This will give you an expected probability for the frequency of each row category. If the variable represented by the columns is fully independent from the variable represented by the rows, then you would expect the same pattern of proportions in each column. This pattern is represented by the probabilities you've just calculated. You can use a second table to record the expected frequencies, or E, for each occurrence. In the observed frequency table, you calculated the proportion, or probability, of each type of defect. In theory, if there is no relationship or dependency between the columns and the rows, then you would expect that the frequency of a given cell would be the direct product of the probability of the row times the total of the column. In other words, you wouldn't expect any given column to show more or less than the probable number in any given row. If it does, you might suspect there is some dependency between variables. To establish the expected values for each cell, you simply multiply the probability for the row by the total for the column. In the third contingency table, you calculate the difference between observed and expected frequencies, square it, and divide by the expected frequency. You do this for each cell in the table, using the values calculated in the previous two tables. Doing so will enable you to analyze how much the observed frequencies differ from the expected frequencies, if at all. Contingency tables approach a business problem as a hypothesis test with two possible hypotheses. The null hypothesis, which states that the two variables are statistically independent, and the alternative hypothesis, which states that the two variables are not statistically independent, or are statistically dependent. In contingency tables, if the chi-square test statistic is equal to 0, this means that the observed and expected frequencies agree exactly and are independent. If it is greater than 0, they do not agree exactly. The larger the value of the chi-square statistic, the greater the discrepancy between observed and expected frequencies. Such a discrepancy indicates some effect or dependency between the variables. The procedure for using contingency tables is similar to the 5-step procedure for all other hypothesis tests. However, there are some additional sub-steps involved in creating the contingency tables. These involve creating the observed, expected, and the square difference of observed minus expected divided by expected tables. You may alternatively choose to use a single streamlined table and record all three values, O, E, and the square difference between O and E divided by E within each individual cell. Suppose that you're part of a team in a pharmaceutical company. You're researching 4 side effects of a medication for high cholesterol on 3 patient populations: those of below average weight, those of average weight, and those who are above average weight. You want to determine whether the distribution of side effects of the medication varies between patient types. You begin by defining the business problem, which can be summarized as this: do the side effects vary according to patient weight? In order to test this hypothesis, your team collects data on the side effects of 516 patients, representing all 3 weight categories. The next step is a sub-step of step 1. You need to create a table for the observed frequencies, in which you will record the observed data. To create a table for the observed frequencies, you list all the levels of patient type as columns and all levels of side effect as rows, including a column and row for the totals. You can then populate each cell with the observed frequencies, O, and total the columns and rows. Finally, you include a column for probabilities. To calculate the probabilities for each row, you divide the total for the row by the total sample size. Let's look at how you calculate probability value to 2 decimal places for 2 of the side effects, fatigue and dizziness. To calculate the probability for the fatigue side effect, you divide the row total, 108, by the total sample size, 516, giving a probability of 0.21. And to calculate the probability for the dizziness side effect, you divide the row total, 156, by the total sample size, 516, giving a probability of 0.30. Remember the aim of the contingency table process: to find out whether the variables, side effect type, and patient weight category are dependent or independent. They are independent if the distribution of side effects for each patient type conforms approximately to the probabilities listed in the last column of the table. Next, you can create a new table to record expected frequencies, using the same row and column headings as for the observed frequencies table. To calculate the expected value for a cell, you multiply 2 values taken from the observed frequencies table, the probability for that row and the total for that column. Let's look at how you calculate each row in the table to find its expected value to 1 decimal place. The expected value for fatigue for patients below the average weight is the total probability for fatigue, 0.21, multiplied by the number of patients in the below average weight category, 113. The product of these values is 23.7. For patients of average weight, the expected value is 0.21 multiplied by 236, or 49.6. And for patients above average weight, it's 0.21 multiplied by 167, or 35.1. The expected value for dizziness for patients below the average weight is the total probability for dizziness, 0.30, multiplied by the number of patients in the below average weight category, 113. The product of these values is 33.9. For patients of average weight, the expected value is 0.30 multiplied by 236, or 70.8. And for above average weight patients, it's 0.30 multiplied by 167, or 50.1. The expected value for poor concentration below the average weight is the total probability for poor concentration, 0.39, multiplied by the number of patients in the below average weight category, 113. The product of these values is 44.1. For patients of average weight, the expected value is 0.39 multiplied by 236, or 92.0. And for patients above average weight, it's 0.39 multiplied by 167, or 65.1. And finally, the expected value for indigestion for patients below the average weight is the total probability for indigestion, 0.10, multiplied by the number of patients in the below average weight category, 113. The product of these values is 11.3. For patients of average weight, the expected value is 0.10 multiplied by 236, or 23.6. And for patients above average weight, it's 0.10 multiplied by 167, or 16.7. There are 2 conditions that must be fulfilled for contingency table results to be meaningful and accurate. First, all expected frequencies must be at least 1. And second, as a mathematical requirement for chi-square calculations, no more than 20% of expected frequencies can be less than 5. The second step is to establish the hypotheses. The null hypothesis is that the observed side effects in different types of patients are statistically independent. In other words, the distribution of side effects is not dependent upon patient type. And the alternative hypothesis is that the observed side effects in different types of patients are not statistically independent. In other words, the distribution of side effects is dependent upon patient type. The third step is to determine the test parameters. One parameter is significance level. Because this test has potential implications for medical practice, the alpha risk level is set low at 0.01. Type of test is another parameter. The type of test is chi-square, which uses the chi-square test statistic. The chi-square test is a right-tailed test. And third is degrees of freedom. You calculate the degrees of freedom as the product of the number of rows minus 1 and the number of columns minus 1. This means that the degrees of freedom for this test is 3 times 2, or 6. The fourth step is to calculate the test statistic. To calculate it, you use the chi-square test statistic formula. You can create a new table to calculate the square difference between O and E divided by E values, using the same rows and columns as previously. You then use the values from the previous two tables to calculate the test statistic for each cell. First, you subtract the expected from the observed frequency, then square the total, and then divide the squared total by the expected frequency. To perform the squared difference between O and E divided by E calculation for the fatigue effect for patients below average weight, you subtract the expected value, 23.7, from the observed value, 20, to give negative 3.7. Next, you square this number to give 13.7. Finally, you divide 13.7 by the expected value, 23.7. This gives a total of 0.58. Similar calculations for average weight and above average weight give 0.39 and 0.04 respectively. You repeat the squared difference between O and E divided by E process to calculate the values for the remaining cells in the table. When you've completed the calculations, each cell should contain the squared difference between O and E divided by E value for that cell. To calculate the chi-square test statistic for the entire table, you simply find the sum of all values in the table. Here, the sum of all the values in the table, rounded to 2 decimal places, is 1.76. Returning to the test involving side effects of medication on different weight categories, the fifth step of the test is to interpret the results. If the chi-square value is 0, then the variables are independent and you fail to reject the null hypothesis. However, you have a result of 1.71, so you need to find out what this means. As usual, there are 2 ways to interpret the result: the critical value method and the p-value method. Each method will lead you to the same conclusions. To interpret the result with the critical value method, you look up the critical value for 6 degrees of freedom and alpha 0.01, which is 16.81. The rejection region is to the right of this number. The test statistic of 1.71 doesn't fall into this region, so the null hypothesis is not rejected. And using an online calculator, you find that the p-value for the chi-square test statistic 1.71 is 0.9443. This p-value is greater than the alpha value of 0.01, so you fail to reject the null hypothesis. Because the test statistic value is greater than 0, and in the rejection region to the right of the critical value, then the null hypothesis, that the side effects in patient types are independent, must not be rejected. You can state the results in this way. Based on the results of this test, I can say with 99% confidence that there is no relationship between side effect type and patient weight category. You can access the job aid contingency table after this video as a guide when you are using contingency tables. You can use contingency tables to determine whether a dependency exists between 2 variables. For example, whether the distribution of defectives varies with product type. A contingency table is a 2-way table consisting of rows and columns. Rows represent one variable and columns represent the other. You can use separate tables to organize the observed and expected frequencies and the square difference between O and E divided by E calculations. In contingency tables, the null hypothesis is that the 2 variables are independent, and the alternative hypothesis is that the 2 variables are dependent. The larger the value of the chi-square statistic, The greater the discrepancy between observed and expected frequencies, and the greater the likelihood that there is a dependency between the variables. Imagine that a production process involves analyzing the variability in the tensile strength of a particular unit based on a number of inputs. Patterns in this data should be quite simple to analyze. But what if the process requires analyzing not only the tensile strength, but also several other response variables, such as the diameter, brittleness, and density of each unit? This information might not be so easy to analyze. That's why you need a tool to help you with analyzing multiple response variables simultaneously. You'll typically use two types of analysis in Six Sigma: univariate analysis and multivariate analysis. Which one you use depends on the variables you want to measure. Statistically speaking, univariate analysis implies analyzing one dependent, response, and one independent, input or predictor, variable at a time. However, there are differing views on the actual number of independent variables for this type of analysis. Multivariate analysis involves multiple variables per observation. It can typically be used to determine the possible influence of many independent variables on one or many dependent variables. Sometimes another term, multivariable analysis, is used to refer to an analysis involving multiple independent variables and a single dependent variable. For the purpose of this course, a simpler definition of multivariate analysis will be used: an analysis that deals with more than two variables simultaneously. Consider a couple of situations where multivariate analysis could be used. For example, you survey a number of households to gather demographic information, and you take several measurements on each household, including the age, gender, education level, and annual income of each household member. Multivariate analysis might lead you to discover a strong link between education and salary, or perhaps all four of these factors. Another situation is a sample of 100 cars. The service manager at an auto repair shop chain takes measurements on these variables for a sample of 100 cars that are 3 years or older: mileage, age of vehicle, service consistency, and noise level. She wants to analyze their impact on two responses: average amount spent on yearly repairs and customer satisfaction scores for each car owner. This data represents a very complex multivariate analysis problem. Imagine that you had to analyze data on 50 characteristics for 300 countries. Obviously, this data would be far too difficult to handle analytically. How could you come to any accurate conclusions? But what if you compared the nations on their economic development, size, and political dimensions? You'd have a much easier time making sense of the data if you could find some common patterns. When you need to reduce data to a manageable level, you can use factor analysis, or FA, which helps you identify the factors that explain variation. A factor is an unobservable, random variable that explains covariances or correlations among measured variables. Factors are underlying constructs, or latent variables, that you can't directly measure or observe. Think about it this way. If two variables have a high correlation, you can conclude that they're redundant and can be reduced to a single factor. Factor analysis can help you simplify a lot of complex data and reduce many variables to a smaller number. It has several key characteristics. FA is primarily used to examine the structure of data by explaining the correlations among variables. It's also used to understand the constructs that underlie the data. It summarizes data into a few dimensions by condensing a large number of variables into a smaller set of latent variables, or factors, which are also referred to as underlying constructs. FA is commonly used in industries that use large data sets, such as manufacturing, banking, and healthcare. Let's review two situations where factor analysis can be used. For example, for customer responses. You want to examine customer satisfaction and feedback on several of a new product's attributes. You conduct a survey among a few randomly selected customers. The survey includes 20 questions, each targeted at a distinctive product attribute. You could use factor analysis to condense the 20 variables to a smaller number of underlying factors. Another example where factor analysis can be used is for test scores. You work in the recruitment department of a large university and have a large data set of applicants' scores on the 10-point admission criteria. You could use factor analysis to condense and analyze them in a more manageable way by narrowing down the large data set to fewer factors. FA involves 4 key steps. The first step is to collect and organize the sample data. Next is to extract the data. The third step is to determine the number of factors to retain, followed by the last step, which is to determine and interpret factors. When you're performing a factor analysis, the first thing you need to do is collect and organize the sample data. Once collected and tabulated, this data takes the form of an n by p matrix. The rows, n, represent the number of observations in the sample, and the columns, p, represent the number of variables. Consider this situation. A toy manufacturer identified 6 variables that affect the quality of each piece: quantity of the liquid plastic poured into the die, temperature of the die, temperature of the liquid plastic, density of the liquid plastic, injecting pressures, and cooling time. The toys sampled would go in the rows in the matrix, and the variables, like temperature and cooling time, would go in the columns. During the first step, you also have to determine which matrix type to choose for your data, correlation or covariance. You'd use a correlation matrix to calculate the factors. When variables are measured by different scales and standardizing variables is desirable, you should use a correlation matrix. This is the type of matrix used in the toy manufacturing example. On the other hand, you'd use a covariance matrix to calculate the factors if you don't want to standardize variables. After you've collected and organized your information, you have to extract the key data during the second step. You do this by calculating and analyzing 2 elements which always come in pairs: eigenvalues and eigenvectors. Eigenvalues, which are negative or positive coefficients, represent the amount of variance explained by each factor. Some of the calculations are done using statistical software. Using the eigenvalues, you identify the principal factors, those factors that account for most of the variance in the data. The last part of extracting the data involves presenting the final values of your eigenanalysis as a table. These numbers represent the variance associated with each factor in the data. In the toy manufacturing example, these would include die temperature, cooling time, and the rest of the variables. Now that your data is organized and you know the eigenvalue of each factor, you have to determine the number of factors to retain. You can do this using 2 approaches, either alone or in combination, which are the Kaiser method or Scree test. The Kaiser method requires you to keep factors with an eigenvalue greater than 1. Each observed variable represents 1 unit of variance in the total variance. When the eigenvalue is greater than 1, each factor represents at least the same amount of variance as one observed variable. When you use a Scree test, you plot factors by eigenvalue and look for a bend and leveling of the curve. Then you keep the factors in the bend before the first point that starts the line trend. Now consider the toy manufacturer again. The Six Sigma team used the principal factors extraction method and charted the results on a Scree test. Based on these results, the team chose the first 3 factors for further analysis. These factors account for most of the variance in the data. The communality for each variable represents the proportion of variability that is explained by the factors. When the communality is close to 1, the variable is better explained by the factors. There's one more consideration during the third step. Once the number of factors is selected, you can use different rotation methods to interpret the factor loadings. There are 4 principal methods which you just need to be aware of. Equimax is used to rotate the loadings so that a variable loads high on one factor but low on others. Then Varimax is used to maximize the variance of the squared loadings. On the other hand, Quartimax is used when your goal is simple loadings. And finally, Orthomax is user-determined based on the given value of gamma. Now you're ready to perform the final step, which is to determine and interpret factor scores using coefficients. The eigenvectors for the retained factors represent the coefficients of the matrix. You use the factor scores to further examine the behavior of the observations. You can also use them if you want to perform another analysis. Here, you examine the coefficient values for each factor variable and attempt to identify values that have high or low loadings for a given component. Access the job aid Performing a Factor Analysis after this video as a guide to the 4 steps. For the toy manufacturing data, the first factor scores are computed from the original data using the coefficients listed under Factor 1 in the table. The communalities for most of the variables, except die temperature and cooling time, are above 0.9, which means that all of the variations in these variables can be almost fully explained by 3 factors. But the communality for die temperature is only 0.89, and cooling time is 0.65, which means some of the variance in die temperature can't be represented by these factors. Using the first table, with the 3-factor and communality columns, you determine that 3 factors account for 89.4% of total variability. The team then creates a table showing the factor score coefficients. The factor score coefficients help explain the factor loadings. Now you can label each factor by examining the various loadings. For instance, for factor 1, the variables that load high are die and material temperature and cooling time. This factor can be labeled temperatures and cooling time. It relates to die and material temperature and the cooling time of the external structure of the toys. The other factors can be measured in the same way. You can reduce data to a manageable level by using factor analysis, or FA. A factor analysis helps you identify the factors that explain variation and can also help you simplify a lot of complex data and reduce many variables to a smaller number. Performing a factor analysis involves 4 key steps. First, you collect and organize the sample data. Then, you extract the data. The next step is to determine the number of factors to retain. Finally, you determine factor scores using coefficients. Access the job aid Performing a Factor Analysis after this video as a reference the next time you need to perform your own factor analysis. Imagine that you're back in school and your teacher is trying to improve your grades in math and physics. He gives you 2 different textbooks to study, which he thinks will help increase your test scores. Although his goal might simply be to improve your grades, your teacher has actually formed a hypothesis that he could test using a multiple analysis of variance, ANOVA. ANOVA is a multivariate tool you can use to analyze data that involves more than one dependent variable at a time. It enables you to test hypotheses about the effect one or more independent variables have on 2 or more dependent variables. In this case, your grades in math and physics, the dependent variables, are both affected by the difference in textbooks, the independent variables. ANOVA is a procedure that's used to test the equality of the mean vectors of more than 2 populations. The technique is comparable to ANOVA for univariate data. However, in ANOVA, the groups are compared on multiple response variables at the same time. There are several other differences between the two. There are some key differences between ANOVA and MANOVA. For dependent variables, ANOVA deals with only one dependent or response variable at a time. MANOVA, on the other hand, deals with 2 or more dependent variables at a time. Regarding the sum of squares, ANOVA uses between and within sums of squares for the treatments and error term, whereas MANOVA uses sums of squares and cross-product matrix between and within groups. Then, for the total, ANOVA uses grand mean sums of squares. MANOVA, on the other hand, uses sum of the square and cross-product matrix total. For significance testing, instead of a univariate F statistic as used in ANOVA, MANOVA determines a multivariate F statistic, or Wilks lambda. And finally, with regards to alpha errors, ANOVA used multiple times across the dependent variables could result in inflated alpha errors. The MANOVA method is used to reduce the alpha risk by having only one test. So, when would you get the chance to use a MANOVA? Well, if you wanted to analyze the overall differences between groups across multiple independent variables, you could use a MANOVA. It would also help you control the experiment-wise error rate. Or you could use it if you were more interested in studying the collective effect of a set of dependent variables than in studying the individual differences. Because MANOVA creates a variate of the dependent variables, you could use it to look at multiple dependent variables as if they were a single construct. It would also give you insight into how the criterion variate could be reduced to a smaller number of dimensions. Now that you understand its characteristics, you can learn how to interpret the results of MANOVA analysis. Suppose the Six Sigma team in the loan processing department at a large bank conducted a multivariate experiment to analyze the relationships between several dependent and independent variables. One such independent variable is training hours. This variable represents the number of training hours taken by the loan processing staff in a year. The values are set at two levels: high, 30 hours, or low, 10 hours. These values are represented by a plus or minus sign, respectively. Another independent variable is the loan amount, which is the average loan applied for by customers for each staff member in a year. The values are either high, $50,000, or low, $10,000. These values are represented by a plus or minus sign, respectively. Then a dependent is the loan processing time, the average time each staff member spent processing each loan over a year. The values are represented in minutes. Another dependent variable is the overtime hours. This variable represents the number of hours recorded for each loan processing agent in a year. The customer satisfaction scores for each agent, also a dependent variable, are continuous scores on a scale from 1 to 10 with decimal values possible. The Six Sigma team members entered the data for each element into their statistical software. Then they ran a ANOVA of the data. This involves running a series of multivariate tests: Wilks, Lawley-Hotelling, Roy's, and Pillai-Bartlett. These tests determine the F-statistic and p-value to help you figure out the statistical significance of the variables. The end results of each test for each variable and interaction are presented in a series of tables. However, a simpler table that summarizes results for just one ANOVA test is given here. It has three sets of statistical values, one for each independent variable and one for their interactions. The values S, M, and N are used in the calculations of the F-statistics. Similarly, other ANOVA tests will give F-statistic and p-values for each variable and their interactions. A detailed discussion of the S, M, and N values is beyond the scope of this course, but you should have a basic understanding of their use. The values S, M, and N are intermediate mathematical values used in the calculations of the F-statistics. With the exception of the S value, they don't have much significance in the decision-making based on ANOVA analysis. They're given more as a convention in many statistical software outputs. The S value is the pooled covariance matrix. It has some importance when you're interpreting ANOVA results. If S is equal to 1 or 2, the F-statistic is exact. Otherwise, it's approximate. In addition, the S value is the minimum of P and Q, where P is the number of responses and Q is the degrees of freedom of the hypothesis. The M value equals the absolute value of P minus Q minus 1, all multiplied by 0.5, where P is the number of responses and Q is the degrees of freedom of the hypothesis. And the N value equals V minus P minus 1, all multiplied by 0.5, where P is the number of responses and V is the degrees of freedom of the error matrix. Finally, the Six Sigma team from the loan processing example examined the p-values for the test statistics. This helped the team judge whether there was significant evidence for variation. The result indicates that the p-value related to the variable training hours is 0.095, which is greater than an alpha value of 0.05 or 5%. For this reason, it's not statistically significant. Similarly, the p-value for the interaction between training hours and loan amount is 0.927, which is greater than 0.05. It's also not significant. However, the p-value related to the second variable, loan amount, is 0.021, which is less than the alpha value of 0.05. This indicates significant evidence for loan amount main effects. In other words, there is enough evidence that the loan amount causes variation in the dependent variables or responses. ANOVA, or Multivariate Analysis of Variance, is a multivariate tool used to analyze data involving more than one dependent variable at a time. It enables you to test hypotheses about the effect one or more independent variables have on two or more dependent variables. Interpreting a ANOVA involves first entering the data into your statistical software. Next, you run a series of multivariate tests, including Wilks, Lawley-Hotelling, Roy's, and Pillai-Bartlett. These tests determine the test statistics, F-statistic, and p-value to help you figure out the statistical significance of the As you know from the sample average, you could estimate the population mean height of residents in a city. The true mean height is an example of a parameter, which is simply a population characteristic that's typically unknown. For instance, the average grade of all college students in the U.S. or the median income of all females under 40 years of age in Brazil are both examples of parameters. Parameters are usually estimated from samples, especially when the population is so large that it's difficult to gather data from every member, as in the previous examples. Parametric tests involve obtaining a sample statistic to estimate the population parameter. When you're making this estimation, the process involves a sample, a sampling distribution, and a population. There are several commonly used parametric tests that test for means, proportions, and variances. These include one-sample and two-sample z-tests or t-tests, paired t-tests, one-way or two-way ANOVA, and f-tests. Even though each parametric hypothesis test has its own unique assumptions, there are a few assumptions common to many parametric tests. For instance, in all parametric tests, it's assumed that observations are drawn from normally distributed populations. One other assumption common to all parametric tests is that the observations should be independent and random. Independent and random graphs will not show any trends in data. Lastly, many tests assume that data has a constant variance across all levels. The scatter of the data points around the line is similar across the entire graphic, and no unusual pattern is visible. Of course, this assumption does not apply to tests that compare variances, such as f-tests. When you're conducting hypothesis tests, it's important that the parametric assumptions hold true. That's because these are the attributes of sampling distributions. If you violate these assumptions in a hypothesis test, you risk drawing conclusions from the sample that aren't true of the population. A parametric test is a powerful method you can use to analyze normal data. However, in the real world, not all data is normal. If you created a histogram of your data, it would resemble a bell-shaped curve if the data was normal. But suppose the curve had two peaks. This would indicate that the data was actually not normally distributed. For instance, many process characteristics display non-normal distributions. Process cycle times, customer arrival times, and wait times are a few. In cases like these, it's important to have an alternative to the typical parametric tests for hypothesis testing. The most significant and most common violation of parametric assumptions is the data distribution being non-normal. So, what exactly do you do in a testing context where you know or suspect that the data violates the assumptions of a parametric test? In other words, that the data has non-parametric characteristics. When the data violates the assumptions of a parametric test, you can use non-parametric tests. In general usage, these refer to hypothesis tests that don't require a normality assumption for the population. Like their parametric counterparts, various non-parametric tests are available to test specific population characteristics using sample data. They may test a central value, such as mean, median, or mode. Or they may test the dispersion, measured by standard deviation, variance, or range. The non-parametric toolkit contains several tests, each specific to measures of central value or dispersion. In any testing situation, then, you have a choice between parametric and non-parametric approaches. How do you decide which is most suitable? Whenever you are confident that the parametric assumptions hold true for your data, your choice should be a parametric test. This is because a key advantage of a parametric test is that if the parametric assumptions hold, the power, or the probability of rejecting the null hypothesis when it's false, is greater than the power of a corresponding non-parametric test with equal sample sizes. Parametric tests are also useful when the sample size is large enough for the central limit theorem to lead to normality of averages. Finally, you may choose to use parametric tests when your data is non-normal, but can be transformed into parametric data. It's vital to note that although the non-parametric test assumptions are typically less stringent than parametric test assumptions, it is a misconception that they carry no assumptions at all, or that they're immune to violations. In fact, there are several important assumptions that must hold true for non-parametric tests. Some tests have particular assumptions, such as specific sample size minimums, that are unique to them. In addition, most non-parametric tests share two core assumptions. That is, data is independent and randomly sampled, and if two or more populations are being compared, the populations assume the same shape or distribution and have the same variance. One final point to note about non-parametric tests is that many of them are very sensitive to outliers in the data, and the presence of outliers can throw the test results off. You might occasionally find the term distribution-free used in the place of non-parametric. Although these terms are often used interchangeably, non-parametric is used to refer to an alternative to parametric tests where the normality assumption is violated. The more commonly used non-parametric tests include the one-sample sign test, one-sample Wilcoxon test, the Mann-Whitney test, Mood's median test, and the Kruskal-Wallis, Friedman, and Levine's tests. Out of these, the two most used in Six Sigma, Kruskal-Wallis and Mann-Whitney, will be discussed. The Mann-Whitney test allows you to perform a hypothesis test to compare two population medians. You can also use it to calculate the corresponding point estimate and confidence interval. Its parametric alternative is the two-sample t-test or z-test. Then, Kruskal-Wallis allows you to perform a hypothesis test to compare two or more population medians for a one-way design. It generalizes the procedure used by the Mann-Whitney test. It's also similar to Mood's median test, since it provides a non-parametric alternative to the one-way ANOVA. You'll notice that while parametric tests typically test the mean as the central value, this is not the case for non-parametric tests, which instead test medians. This is because the median is a more robust estimate of the central value of a distribution. This course will further examine two common tests of population medians, the Kruskal-Wallis and Mann-Whitney. But first, let's look at the pros and cons of non-parametric tests and when to use each test. Like any method for analyzing data, non-parametric tests have their own unique advantages as well as limitations. First, consider the benefits of using non-parametric tests. The main advantage is that, in many cases where parametric tests are inappropriate or impractical to use, non-parametric tests might be the only option. Non-parametric tests are also simple, quick to apply, and intuitive. This has the benefit of reducing the time and resources needed to collect and analyze data. Another advantage is that it reduces data collection time and costs is the fact that non-parametric tests can be used with small samples. They are also more robust. Because assumptions are less stringent and easily satisfied, non-parametric tests are often more robust than the parametric equivalents. One last advantage is that, in some cases, non-parametric tests can handle ordinal and nominal data because most of the tests work with rank-ordered data rather than actual values. This is useful when it's difficult to obtain quantitative data. Now that you have a good understanding of the advantages non-parametric tests have to offer, you can move on to their limitations or drawbacks. One limitation of non-parametric tests is that most require the data to be rank-ordered before the test statistic can be calculated. This creates an extra step in the analysis process, and a lot of information is lost in the process of rank-ordering the data if it originally was continuous data. Another limitation is a false sense of security. Although assumptions in non-parametric tests are less restrictive, they still must hold. Sometimes test users think the tests are immune to assumption violations and outliers, but this is a false sense of security. A point to note is that assumption violations and outliers have actually been proven to have a large impact on Type 1 and Type 2 error rates in non-parametric tests. As you can tell, non-parametric tests can be very useful, but you should keep in mind that they do have their drawbacks as well. By considering both the advantages and limitations of non-parametric tests before you begin your analysis, you can help ensure you choose the testing method that best meets your needs. Your choice of test, whether parametric or non-parametric, depends on the situation. You'll recall that you should choose a parametric test if the data is known to be normally distributed. But there are other considerations for choosing a test as well. For instance, you might consider using a parametric test for data that is non-normal in the certain situations. For instance, you know that the data fits a particular non-normal distribution, such as the exponential distribution, and the assumptions for that distribution hold true. In such cases, the formulas and calculations for that particular distribution could be used to analyze the data. Another situation is that the data is non-normal but can be transformed. On the other hand, you should consider using a non-parametric test when the data is distinctly non-normal and can't be transformed to give it a normal distribution. You should use a non-parametric test. A parametric test would give you unreliable results in this case. You should also use a non-parametric test when the data is from an unknown distribution, or from a distribution that isn't suitable for parametric methods. Because non-parametrics are considered distribution-free, you don't necessarily have to confirm whether the data is normal or non-normal. Normality tests aren't always feasible, because collecting the data requires a large effort and expense. If you suspect the data might be non-normal, and the risk of getting misleading results from a parametric test performed on non-parametric data is considered too great in your situation, then you should choose a non-parametric test. You can use a non-parametric test when the data is nominal or ordinal. Non-parametric tests generally rank order the data before testing, so ordinal data is ready-made for this type of test. This consideration is of secondary importance relative to the normality or non-normality of the data. Lastly, when the distribution of a large population is unknown, sample size may be a factor in your decision to use a non-parametric or a parametric test. If your sample size is too small, you will not be able to rely on central limit theorem to assume that the sample statistic estimates the population parameter. In that case, you will weigh your risks and might choose to compromise the power of the test rather than risk making a costly mistake based on unreliable parametric test results. A small sample size is not a necessary or sufficient condition for choosing a non-parametric test, but it should reinforce your decision to choose a non-parametric test when you can't attest to the data's normality. There's one overarching point to remember about choosing a test. If you have a choice between using a parametric or non-parametric test, and you're certain the assumptions for the parametric test are met, the parametric test is the more powerful option. It will give you a better chance of finding any special variations in the processed data. But if the parametric test isn't appropriate, you can be certain that a non-parametric test is a reasonable substitute. Once you have determined that a non-parametric test is appropriate, you will use your particular analysis needs to choose the right test. Your choice will depend on how many different samples you are testing, 1, 2, or more than 2, and whether you wish to test the central value or the dispersion of the populations. Recall that the Mann-Whitney compares 2 samples only, and the Kruskal-Wallis compares 2 or more samples in a one-way analysis. A parameter is a numeric quantity that's typically unknown and describes a certain population characteristic. Parametric data refers to a distribution that's assumed for a population. You perform a parametric test when you can make a parametric assumption, such as normality. A parametric test is a powerful method you can use to analyze normal data. But when data distribution is non-normal or unknown, you use a non-parametric test. The most significant and common violation in data analysis is the data distribution being non-normal or non-parametric. When this is known or suspected to be the case, non-parametric tests should be used to test specific population characteristics from sample data. There are 2 broad categories of non-parametric tests: tests of population location or central value, and tests of spread or dispersion. Common non-parametric tests include Sign, Wilcoxon, Mann-Whitney, Moods, Kruskal-Wallis, Friedman, and Levine's. Non-parametric tests have certain advantages as well as limitations, and it's important to consider both before beginning your analysis. Your choice of test, whether parametric or non-parametric, depends on the situation, and there are several considerations involved with determining the best test to use. If you're certain the assumptions for the parametric test are met, the parametric test is the more powerful option. But if the parametric test isn't appropriate, you can be certain that a non-parametric test is a reasonable Imagine that you're a Six Sigma black belt at a mechanical components manufacturer and you're analyzing the bearings provided by 3 different suppliers. You want to determine whether the bearings from at least one supplier have significantly higher diameters but aren't sure which non-parametric test to use. This situation exemplifies a good time to use the Kruskal-Wallis test. This test can help you determine whether 2 or more independent samples come from populations that have the same location or central value. The Kruskal-Wallis test is a non-parametric alternative to an analysis of variance, or ANOVA. It's used when the underlying population distribution is unknown or is known to be non-normal. This test can benefit organizations by allowing them to compare the performance of samples, helping them determine whether there's a difference in the population the samples come from. Consider some examples where the Kruskal-Wallis test could be useful. For example, it could be used if you wanted to compare 4 suppliers' products before making a purchase. Another example where it could be useful is if you wanted to compare the measurements of 5 different machine operators. And a final example where the Kruskal-Wallis test could be useful is if you were a producer of milk and wanted to determine whether the bacteria in milk are the same from shipment to shipment. In your own analysis projects, you'll sometimes have to decide between various non-parametric tests. How do you know which to use in a given situation? Well, consider a situation where you're deciding between a one-way ANOVA and Kruskal-Wallis, for instance. ANOVA might be a better choice if the population is known to be normal. This is because Kruskal-Wallis isn't as powerful as a one-way ANOVA, and ANOVA itself is quite robust against deviations from normality. What about choosing between Kruskal-Wallis and Moore's median test? Both tests are used to compare 2 or more independent samples and are useful non-parametric alternatives to the one-way ANOVA. However, there's one key difference. The Kruskal-Wallis test uses the sum of difference between mean ranks of samples as the test statistic, whereas the Moore's test statistic relates to the number of values that are larger or smaller than the median value, but not their actual distances from the median. This is why the Kruskal-Wallis test is a more powerful alternative to Moore's median test for analyzing the variance between 2 or more populations. It's also more powerful than Moore's for data with many distributions, including data from the normal distribution, but is less robust against outliers. There will be cases where the Kruskal-Wallis test isn't appropriate. It only works under 4 conditions. One condition is that samples must be independent and random. Another condition is that populations must have the same distribution or shape. Third, the value for n, which is the size of the sample, must be greater than or equal to 5 for each sample. And a final condition is that populations must have equal variances. It's not enough to know when to use the Kruskal-Wallis test. You also need to understand how it works. First, you pool the values in all the samples being studied and assign a rank to each value. Then you sum the ranks for each sample to determine whether the medians are approximately equal or significantly different. Kruskal-Wallis requires that you use the test statistic H and find the critical values on the chi-square tables. Now that you have a good understanding of when to use the Kruskal-Wallis test, you're ready to learn the steps involved in conducting one. This entails performing the same steps as you do with other hypothesis tests. You begin by defining the business problem. The second step is to establish the hypotheses. The third step involves determining the test parameters. In the fourth step, you calculate the test statistic. And in the final step of the test process, you interpret the results. Considering an example is the best way to learn how to use the Kruskal-Wallis test. Remember the scenario from the beginning of the video? You'll recall that you're a Six Sigma black belt who works at a mechanical instruments manufacturer and are analyzing the diameters of bearings provided by 3 different suppliers. You define the business problem. You want to determine whether at least one supplier has significantly higher bearing diameters. Then you collect 10 random samples from each supplier's material and measure the diameters in centimeters. You're not certain about the population's distribution for each supplier, but the populations have the same shape and equal variances. Next, you establish the hypotheses. The null hypothesis is that the population medians for all 3 suppliers are equal. Or, to put it another way, the median for bearing diameters is the same for all 3 suppliers. And the alternative hypothesis is that the population median for at least one supplier is greater than the others, or that the median bearing diameter is significantly greater for at least one of the suppliers. You should note that the alternative hypothesis can be left-tailed, right-tailed, or two-tailed. In this case, it's right-tailed. The business problem has been defined and the hypotheses established, so you next have to determine the test parameters. This involves defining degrees of freedom and the alpha value. The number of groups or levels of the factor being studied is represented by the letter K. In this case, there are 3 levels, the 3 suppliers. Degrees of freedom for a Kruskal-Wallis test is calculated by subtracting 1 from K. So 3 minus 1 gives you a degree of freedom of 2. You then determine the second test parameter, the alpha value, which is typically set at 0.05. Now you move on to the fourth step, calculating the test statistic. This procedure entails performing 3 tasks. First, you use a tally table to assign a rank to each data value based on its rank among all data values from all samples. So the first bearing diameter in the table, 1.01, is ranked number 1 since it's the lowest of all the values. This diameter only occurs once in all the readings, so it's assigned a frequency count of 1. What if a diameter occurs more than once? In this case, if 2 or more observations are tied, the average rank is assigned to each. For instance, the diameter 1.06 occurs 4 times. Instead of ranking each reading, you'd assign this value the average rank, 10.5. The second task when you're calculating the test statistic is to add up the ranks for each group. For instance, in the case of supplier A, the total of all the ranks is 144.5. Computing the test statistic, H, is the final task during this step. The test statistic formula is a function of sample size and includes the sum of the average ranks of all tables. The letter N represents the total number of observations. N subscript j is the size of sample j, and uppercase R subscript j is the sum of the ranks in sample j. The first thing you have to do is divide 12 by n times the outcome of n plus 1. Next, you add the ranks for a sample and raise it to the power of 2, and divide this number by the sample size. Once you've done this for each sample, you add all the results together. Then, you multiply this number by the result of 12 divided by n times the outcome of n plus 1. Finally, you subtract 3 times the outcome of n plus 1. Now, return to the example from earlier in the topic. When you compute the test statistic, here are the steps you take. First, you figure out the middle part of the formula by summing the squared rank sums divided by the sample size for each sample. For supplier A, the total is 144.5. For supplier B, 151. And for supplier C, 169.5. Placing each total into the formula, the sum of all 3 works out to 7,241.15. Next, you divide 12 by n multiplied by the outcome of n plus 1. You already know the value of n. It's simply the total number of observations, 30. Then you multiply this number by 7,241.15, the value found in the previous step. Finally, you subtract 3 times the outcome of 30 plus 1. This gives you a test statistic of 0.434. Finally, you perform the last step in a Kruskal-Wallis test, which involves interpreting the results. At this point in the process, you have a choice. You can either apply the critical value method or the p-value method to draw conclusions about the equality of the means. If you're using the critical value method, you use the chi-square chart. But in this case, you chose the p-value method. Generally, the p-values are found using statistical software. Because this is a one-tailed test, you find the degrees of freedom and the corresponding alpha value. In this case, the p-value is 0.81. If the p-value is less than alpha, you should reject the null hypothesis. On the other hand, if it's greater, you should fail to reject the null hypothesis. But what does all this mean? Since the p-value is greater than alpha in your situation, the null hypothesis will be retained. There isn't enough evidence to believe that the population medians aren't all equal. In other words, the difference in the median values of the suppliers could be due to chance, and there isn't a statistically significant difference among them. Now, what if you had achieved the opposite result? If the null hypothesis had been rejected, you could state with 95% confidence that the median value is greater than the others for at least one of the suppliers. The Kruskal-Wallis test is a non-parametric alternative to an analysis of variance, or ANOVA, that can help you determine whether two or more independent samples come from populations that have the same location or central value. Like other hypothesis tests, Kruskal-Wallis involves performing 5 key steps. First, you define the business problem. The second step is to establish the hypotheses, and the third step is to determine the test parameters. The final 2 steps are to calculate the test statistic and interpret. A major university decided to offer its students the choice between lectures in a traditional classroom setting or a new online format. After the online courses had been offered for a year, the university conducted a study to find out if there were differences in grades among students who received computer-based training as opposed to those who received traditional lectures. Can you determine the best non-parametric test to use in this situation? If you thought the Mann-Whitney test would be the most appropriate, you'd be right. It's a non-parametric test you can use when you want to know if two populations are similar. It tells you if they have the same median. You might sometimes find this test referred to by one of its 2 aliases, the Mann-Whitney-Wilcoxon test or the Wilcoxon rank-sum test. Before moving on to the more technical aspects of the Mann-Whitney test, consider a couple of situations where it could be used. For example, you could use it when you want to determine whether the central value is equal between 2 populations. Another situation where the Mann-Whitney test could be used is when your population's data distribution is non-normal or unknown. Like any parametric 2-sample test for means, the Mann-Whitney test allows your company to compare the central value of 2 populations to determine if they're significantly different. It's also similar to analysis of variance, ANOVA, or to non-parametric equivalents, such as Kruskal-Wallis. However, the differences are that the Mann-Whitney test compares medians rather than means, and it is limited to comparing only 2 rather than multiple populations. How exactly can the Mann-Whitney test benefit your organization? Well, it could help answer 3 questions. Does the process or product vary between 2 shifts in a manufacturer? Has significant change occurred in a process as a result of an improvement initiative? And does the product or equipment differ for 2 suppliers? To better understand when to use a Mann-Whitney test, you should examine a few scenarios where it wouldn't be appropriate. First, suppose the Six Sigma team at a paper manufacturing plant is comparing the output of 2 machines where the data is known to be normal. In this case, the team should use a parametric test, and the Mann-Whitney test wouldn't be appropriate. It should be noted that a parametric test would also be suitable with non-normal data that could be transformed to fit a normal distribution. Consider another scenario. 2 brands of computer are in use at a hospital, and the Six Sigma team wants to compare the variances of the 2 non-normal populations to determine if there's a difference in performance between them. The Mann-Whitney test would not be appropriate because it is a test of population medians, not variance. In this case, a non-parametric test for variance, such as Levine's test, would be suitable. Now consider a final scenario. A school is researching the academic performance of its pupils on the National Aptitude Test with a published average score of 70. It's believed that student test scores are not distributed normally. The principal of the school suspects that the student test average is lower than the standard and assigns the quality assurance team to determine if the difference is significant. In this case, the Mann-Whitney test would not be appropriate, as the situation would be better suited for a non-parametric 1-sample median test measuring whether a sample median differs significantly from a hypothesized value. Another point to make about the Mann-Whitney test is that it's important to understand the assumptions under which it works. The first is that the data source in each population is from independent and random samples. The second is that the populations have the same or similar distributions or shapes and equal variances. Finally, the value for n subscript 1, the size of the first sample, must be less than or equal to the size of n subscript 2, the second sample. The The mechanics of the Mann-Whitney test are similar to those of the Kruskal-Wallis test in that they both involve ranking all the data values. However, in this case, the test statistic, M, is only the sum of the smaller sample. The test result is then compared to a critical value that is found in the Mann-Whitney critical value table. Conducting a Mann-Whitney test involves performing the same steps as you do with other hypothesis tests, which you should already be familiar with. The best way to learn how to use the Mann-Whitney test is to consider an example. Imagine that you're a Six Sigma black belt at a large inbound call center. You're trying to determine if there's a significant difference in the amount of time taken by two shifts, the day shift and the night shift, to resolve customer queries. This is the first step in your test. You're defining the business problem. Specifically, you want to know if customer service representatives working the night shift take less time to resolve queries than representatives working the day shift. The first thing you do is collect data. You decide to take 9 random samples of call durations from the night shift and 10 from the day shift. You list the call durations, rounded off to the nearest minute, in a table. You can assume that the population data for each shift isn't normally distributed, and that the populations have the same shape and equal variances. You can also assume that your test fulfills the other conditions necessary for it to work. The data from each population is from independent and random samples, and the first sample is smaller than the second one. Next, you establish the hypotheses. The null hypothesis is that the population medians for both shifts are equal, or, to put it another way, the median for call duration is the same for the day shift and the night shift. And the alternative hypothesis is that the population median for one shift is different, or more specifically, that the population median of the call duration for the night shift is less than that of the day shift. You should note that, like other hypothesis tests, the alternative hypothesis can be left-tailed, right-tailed, or two-tailed. In this case, it's left-tailed. The business problem has been defined and the hypotheses established, so you next have to determine the test parameters. This involves defining degrees of freedom and the alpha value. For some other tests, you have to actually calculate the degrees of freedom. However, in the case of the Mann-Whitney test, you simply find the values for each sample size in the Mann-Whitney table. You'll recall that sample 1 equals 9 and sample 2 equals 10. The alpha value is set as the standard value for statistical significance of 0.05. Now, you move on to the fourth step, calculating the test statistic. This procedure entails performing 2 tasks. First, you use a tally table to assign a rank to each instance of a data value based on its rank among all data values from all samples. For instance, the first reading in the table, 2, occurs 5 times. When 2 or more observations are tied, you simply assign the average rank to each. So in this case, the reading 2 is given the rank of 3. The second task when you're calculating the test statistic is to add up the ranks for the original data. If you remember this procedure from the Kruskal-Wallis test, you'll recall that the table had columns for ranks for all the samples. But in the case of Mann-Whitney, there's only one column for ranks. That's because the Mann-Whitney test only requires that you add the ranks for the smallest sample. Once you've calculated the sum of the ranks for the smaller of the 2 samples, you've found the test statistic, M. In this case, the value for M works out to be 117. These 4 steps give you the information you need to make sense of the data you've collected and perform the final step in a Mann-Whitney test, which is to interpret the results. The Mann-Whitney critical value table was developed specifically for this test. The letters ML represent left-tailed tests and MR represent right-tailed tests. The table is simple to use. You find the size of sample 1, which is 9, and sample 2, which is 10. The number corresponding to their intersection on the chart is the critical value. So in this case, the critical value is 66. You'll recall that the null hypothesis is that the population medians for both shifts are equal. Because the test statistic, 117, is greater than the critical value, 66, for this left-tailed test, you have to fail to reject the null hypothesis. What does this mean for your project? Basically, because there's not enough evidence to reject the null hypothesis, you have to retain the null hypothesis that the 2 population medians are equal. In other words, there isn't any statistically significant difference between the call durations of the night and day shifts, and any difference that appears might be due to mere chance. Now, what if you had achieved the opposite result? If the null hypothesis had been rejected, you could state with 95% confidence that the median call duration of the night shift is less than that of the day shift. The Mann-Whitney test is a non-parametric test used when you want to know if two populations are similar with respect to their central values, specifically their medians. The test works only when three conditions hold true. The data from each population must be independent and random. The populations must have the same or similar distributions and equal variances. And the first sample must be less than or equal to the second sample. The Mann-Whitney test follows the basic procedure for hypothesis testing. The procedure for finding degrees of freedom is slightly different, however. You simply find the values for each sample size in the Mann-Whitney table. To calculate the test statistic, you calculate the sum of the ranks for the smaller of the two samples.